Hi guys, I am Neeraj Toshniwal and I am currently studying in IIT Bombay doing my BTech in computer science, and I secured an AIR of 21 in IIT JEE 2009 and also was a gold medalist in National Chemistry Olympiad 2009. So I am here to teach you inorganic chemistry, and today the topic will be the chemical bonding. So before starting this topic, I just want to shed some light on the importance of the chemical bonding as far as the JEE is concerned, and also its relation to the other important of the topics of inorganic chemistry is concerned. So firstly, chemical bonding in the JEE, chemical bonding is the most number of marks, most number of questions comes from the chemical bonding in the inorganic chemistry part. So from this you can state what is the importance of this topic, chemical bonding. And also during this chemical bonding we are also going to study some properties of S block elements, P block elements, D and F block elements. So we will cover little bit portion of the S, P, D and F block elements also in this chemical bonding chapter. So during this topic we will learn how to write a structure given the molecular formula, how to predict its hybridization, how to predict the bond length and the bond strength, compare bond length and bond strength of the molecules given. So let us start the topic chemical bonding. So before starting, what do you mean by the chemical bond? The first question which arises is, what do you mean by the chemical bond? So the chemical bond is the attractive force that holds the constituents like atoms, ions together in different species is known as chemical bond. And now the second thing would be, why is the chemical bond is formed? Why is there a need to form it? Definitely the chemical bond would be formed only if the molecule which is resulting from it would be stable. So how do you define the stable molecule? Stable molecule, stability of any constituent, any species can be defined as if it has the lower energy than its individual atoms. For example, if the equation is A is a gaseous element and plus B is a gaseous element, and they results in the element Cg. So the energy change involved in this process would be the delta reaction, I should say, of this equation would be is equals to energy of C minus energy of A plus energy of B. So this reaction, if this delta reaction would be negative, that means the reaction is exothermic. So in this case only this reaction will be spontaneous. So by this I mean that if E of Cg would be less than the sum of the E of Ag plus energy of Bg, then only this reaction will take place. So the chemical bond formation takes place to lower the energy, or I should say the product has a lower energy as compared to the sum of the constituents. That's why chemical bond is formed. Now chemical bond, during the formation of chemical bond, only the outer valence shell electrons are involved, not the inner shell electrons. Let's say for example I will say aluminium has the electronic configuration of 1s2, 2s2, 2p6, 3s2, 3p1. So it has 3 valence electrons, 2 in the 3s subcell and 1 in the 3p subcell. So only these 3 electrons will participate in the bonding. These 10 electrons will have no effect as far as the chemical bond formation of chemical bond is concerned. So only these 3 valence electrons will be present, and this chemical bond will be formed to complete it octet, which means the aluminium will either try to gain 5 electrons to achieve the configuration of argon, or will try to lose 3 electrons to achieve the configuration of neon, because as we know that the electronic configuration of neon or of noble gases is quite stable as compared to other elements. So that is why the chemical bond formation will be taking place. So first thing is that Lewis proposed a structure. He said that every element tries to achieve the stable octet. That means in the last subshell it will have the 8 electrons. In the last valence shell it tries to have 8 electrons. It tries to have the stable octet configuration either by transferring its electron to other or by sharing its electrons. So by transferring the electrons, we in the later part of this lecture we will see that the transference of electrons, if it is achieving a stable octet by transferring the electron, then it would form an electrovalent bond, and if it is sharing the electron, then it will form a covalent bond. So how do you do it? Now I will define the Lewis structure. So Lewis structure is drawn. Let's say if I want to draw the Lewis structure of beryllium. So we know the beryllium has an electronic configuration of 1s2, 2s2. So the Lewis structure is drawn which shows only the valence electrons present, that is the electrons which can actively participate in the bonding. So here beryllium, if you want to draw the Lewis structure for beryllium, you will draw the symbol Be, and we know that there are two valence electrons, so you will draw it something like this. So this is the Lewis structure for beryllium. Let's say you want to draw the Lewis structure for fluorine. We know the fluorine has the electronic configuration 1s2, 2s2, 2p5. That is, it has 9 electrons, so 1s2, 2s2, 2p5. So it has the 7 valence electrons, 2 in the 2s subshell and 5 in the 2p subshell. So fluorine will have the Lewis structure of this, something like this. So the Lewis structure shows the valence electrons present, the valence electron that can actively participate in the bonding. So yeah, this is the thing. Also, now what is the significance of Lewis structure? So Lewis structures help us determine the group valence of an electron. Now what do you define, what do you say as group valence of an electron? So group of an electron, or I should say group valence of the electron, is equal to the number of valence electrons present, or 8 minus the number of valence electrons present. Now the question arises, when is it equal to the number of valence electrons present, and when it is equal to the 8 minus number of valence electrons present. So if the valence electrons are greater than 4, then it is equal to 8 minus number of valence electron. The group valence of the element would be equals to the 8 minus valence electrons, and if the valence electrons are less than or equal to 4, it would be equals to the number of valence electrons. So this is how this is helping us in determining the group valence of an electron. Now, so as I was talking about the transferring of an electron, it results in an ionic, or I can say electrovalent bond. So let me state some what is an electrovalent bond. So bond formed as a result of electrostatic attraction between the positive and negative ion is known as the electrovalent bond. Now what are the factors on which the formation of electrovalent bond depends? So one of the factor, which is as we have discussed in the basic module of periodic properties, is that it depends on the ionization energy. The electropositive element which is taking place in it should have the first ionization energy quite low. That is, if M is going into M, I should say G is going into M plus G plus electron, so the M should have the first ionization energy very low. How does this help in determining the electrovalent bond? Because it is available for losing that electrons by providing a very little energy. Therefore, low first ionization energy for the electropositive element, the element which is going to lose electron, is a favorable condition for the formation of electrovalent bond. Second would be negative electron gain enthalpy for the electronegative element. The element which is going to accept the electron should have the very negative electron gain enthalpy. Very negative electron gain enthalpy. This will this is one of the factor also towards that. See, if there is a high electronegative difference between the combining atoms, then there is a higher chance that it has more ionic character. Because you can say that I have also told it in the basic module of periodic properties that ionic character in that covalent compound is determined by the 16 delta X plus 3.5 into delta X raised to whole square. This percentage of ionic character is determined in any covalent compound. So if delta X is higher, definitely it would lead to more of the ionic character. So the difference in electronegativity, more would be the ionic character. The D and the nu is that the lattice enthalpy should be very high. What do you mean by lattice enthalpy? Lattice enthalpy is if there is a metal, this ionic electropositive metal M plus G, and there is x minus g, and this goes to mx forming as solid. So this equation, this lattice enthalpy should be high. So lattice enthalpy is defined as the energy required to break 1 mole of the lattice completely into its gaseous constituents. This is how lattice enthalpy is defined. So if the lattice enthalpy would be very high, then combining energy, the energy released would be very high in this case, and this will favor the formation of electrovalent bond. So now the next question arises, what are the conditions, what are the factors on which the lattice enthalpy depends? First factor for the lattice enthalpy would be that the lattice enthalpy is directly proportional, or I should say inversely proportional to the R plus R minus, where R plus and R minus, this whole quantity is the internuclear distance or interionic distance. So if ions are close together, you can say that lattice enthalpy would be very high, but if the ions are far together or are far away from each other, then the lattice enthalpy would be low, because it would be easier to break the forces between them as compared to when they have very less interionic distance. Another factor on which the lattice enthalpy directly depends is on the charge on anion and cation. Definitely more the charge on the anion or more the charge on the cation, the forces that are holding them together would be very high, and it would be very difficult to break them apart. So the lattice enthalpy in that case would be very high. Lattice enthalpy also depends on the coordination number of the compounds. Coordination number of a cation is defined as the number of anions that is surrounding that cation, and coordination number of an anion is defined as the number of cations that are surrounding that atom. You will know more about the coordination number in the coordination compound. So for the time being, just this is one of the factors also which I want to mention, because I don't want to understate anything. So lattice energy also is directly proportional to coordination number also. Yeah. So this was things. So how do you determine the lattice energy? The next thing would be the determination of lattice enthalpy. So for the determination of lattice enthalpy, there is a cycle which is known as the Born-Haber cycle. Born-Haber cycle relates different energy steps. It relates the different energy steps to the one common thing. So Born-Haber cycle is a thermochemical cycle which is based on Hess law of constant heat summation. What do you mean by the Hess law? Hess law states that the net enthalpy change in a reaction would be always remain same, whether if it is going to its position in one step or in many steps. For example, let me say that if there is a solid, M solid, plus there is a gaseous state, and these both are combining to give me an lattice mxs, and let's say it has the energy change involved delta hf. So what are the steps which are leading from here to here? The steps can be one. First, I would try to convert it into a gaseous atom, which would mean that I have to supply some delta H sublimation. Mind you, the sublimation means that directly converting a solid into gaseous state. So I have to supply some sublimation energy to convert it into solid to gas. Then I have to first convert it into the ionic state, that is the cation, form a cation M plus gaseous. So I will have to supply the ionization energy 1 of M, so it would be my electron. From here I have to first decompose it, that is H dissociation. I have to dissociate the X2 into X. So I have to supply, because there are half more present, so half into H dissociation would give me the X gaseous, and then I have to supply the electron gain enthalpy, that is I have to add an electron, first electron gain enthalpy, to convert this into X minus G. Now this both will combine and give me the mxs, and this is represented as delta H lattice energy. So what does Hess law says? Hess law says that delta HF, that is the total enthalpy change, would be equal to the delta H sublimation plus delta plus first ionization energy of M plus half of delta H dissociation of X plus first electron gun enthalpy of X and plus the lattice energy. So if you know the change, if you know the energy involved in this process, that is delta HF, and you know all the variables, sublimation, ionization, first ionization energy, delta dissociation and electron enthalpy 1, you can easily calculate delta H lattice enthalpy, that is lattice enthalpy from this reaction, and this is how we calculate the lattice energy from the Bond-Haber cycle. So it helps in determining us the lattice enthalpy of any solid. Yeah. So the next concept which comes into chemical bonding is of the hydration. So first thing would be, what do you mean by hydration? That is attachment to any of the cation or any of the anion, I should say, would be the hydration. So all salts dissolved in water producing cations and anions in the aqueous solution. So what happens that if you are more the small the size of the hydrated ion, more will be its electric mobility. So whenever a salt is dissolved in water, it breaks up into ions and they are free to move in that. So the ability of the ions to move is called as the electric mobility. So more smaller would be the ion, more would be its electric mobility, or I should say more stability, more smaller the hydrated ion, more smaller the size of the hydrated ion, more would be its mobility. So let's compare two ions, Li plus and Cs plus, and I can say, writing an AQ, if when I write it as AQ, this would mean it is in aqueous form or it is in hydrated form, it is dissolved in water. So we know that this belongs to the alkali metal group. So if I would say that Li plus in the solid form or in the gaseous form and Cs plus in the gaseous form, compare the radius of the Li plus and Cs plus, so we would know that going down the group, the cation, the size of the cation increases, so the radius of Cs plus would definitely be greater than the Li plus. So but here the size of the hydrated Li plus is greater than the size of the Cs plus, so the mobility of Cs plus in turn is greater than that of the Li plus. Now why does this happen? So more smaller the ion is, more would it be the probability of it to be heavily hydrated, because the concentration of the positive ion is on the smaller area, so concentration is more, so it will attract the lone pairs of the water molecules is much stronger as compared to that of Cs plus. So what the structure of Li plus is a very peculiar structure in the aqueous form, I should say, is a very peculiar structure. What happens is something like this, that there is a primary layer and there is a secondary layer. So what happens in primary layer, that there is a Li plus, or you know the Li plus has an electronic configuration of 1s2, so it has 2s and 2p, both orbital vacant, so it has 4 vacant orbital. So hydrogen and H2O has a lone pair. What is a lone pair and what is a bond pair, it will be discussed in the later part of this chapter, in this lecture. So it is joined to this, something like this. So 4 lone pairs, Li plus is joined to 4 molecules of water through lone pair. So this forms the primary layer of the hydrogen atom. Now there is some positive charge on Li plus, so the oxygen of this is, and oxygen has a delta negative charge, so it is something you can, so dipole interaction is also taking place from here, from the oxygen delta minus H. So there it is connected to 4, or I should say 8 water molecules. The Li plus is connected to 8 water molecules, so its structure is quite peculiar. So this second layer of 4 molecules is a secondary layer, and this first is the primary layer. So this is the primary layer, this layer is the primary layer and this constituents of these four is the secondary layer. So because of this, it's heavily hydrated, and that's why its electric mobility is less as compared to CS plus, and also the hydrated size of Li plus is greater than as compared to that of CS plus. So it is a very good question that can be asked in JEE. You have to look at whether you have been asked to compare the size of Li plus and CS plus anion or in cation in the gaseous state or in aqueous state. If it is in aqueous state, then Li plus would be greater than the CS plus, and if it is in gaseous state, then it would be Li plus would be less than CS plus. So this is the hydration order for the alkali metal group. So the next I would be talking about is the hydrolysis. The one that we talked about now was the hydration, and the other one was the hydrolysis. So what do you mean by hydrolysis? Hydrolysis means reaction with water which ultimately lead to the breaking of HOH bond into H plus and OH minus ions. So what does hydrolysis would mean? So hydrolysis can be done in two ways. One is by covalent bond formation, by coordinate bond formation, and the other is by H bond formation. So first I will take the example of coordinate bond formation. What do you mean by the coordinate bond formation? So coordinate bond formation would mean that the water molecule has linked to an element which has vacant orbitals present, vacant d orbitals or some vacant orbitals present. Let's say if I take an example of SiCl4. So SiCl4 has the tetrahedral structure, which I will tell you later how to predict the geometry of the molecule given. So it is SiCl4. So when it has a vacant d orbital, because silicon has the electronic configuration of 1s2, 2s2, 2p6, 3s2 and 3p4. This is the electronic configuration. So in 3, when the principal quantum number is 3, there are also vacant d orbitals present in here. So the hydrogen, oxygen has some lone pairs, has 2 lone pairs, so it attacks the silicon through the coordinate bond formation, and this hydrogen and chlorine comes out. So the resulting would be the SiOH 3Cl on it plus HCl. So this is the breakage of water molecule into hydrogen, H plus and OH minus ions. So that's why it's known as hydrolysis, and one Cl atom is replaced by the OH and HCl is formed. Similarly, the other 3 Cl atoms can also be removed, and it would lead to the formation of SiOH whole 4. However, it is found that it is an unstable species. So this is not a very favorable condition in the favorable reaction in the forward direction. So this was through the coordinate bond formation. The other is through the hydrogen bond formation. So there are some molecules in which there are no vacant orbital is present, but because of their attraction to their lone pair, because of presence of their lone pair, they attract the hydrogen molecule of hydrogen atom of the water molecule and get attached to that. Something like so ammonia NH3 has one lone pair here. So its hybridization is with 3. So one water molecule, this hydrogen has a delta positive charge and it is completely electron, so it is having the pure negative charge. So there is an interaction between the lone pair and this hydrogen, which is some delta positive charge, and this led to the breakage of this bond, and the resulting would be the NH4 plus ion, ammonium ion it should be say, plus the OH minus ions. This also leads to the breakage of this H minus OH minus. So this is also hydrolysis. So there are two types in which the hydrolysis can be done, either through the covalent bond formation or by the H bond formation. Covalent bond formation takes place when coordinate bond formation takes place when there is a vacant orbital present as in case of SiCl4. Yeah. So next I will talk about some properties of electrovalent compounds. In the physical state, the electrovalent compounds mostly exist in solid state or in molten state, but most of them were not found in the gaseous state. The second is they show isomorphism. So what do you mean by isomorphism? That is, in the crystalline structure of two molecules are same, then it is said to be isomorphism, and isomorphs, and the phenomenon shown is isomorphism. So let's say FeSO4 dot 7H2O and MgSO4 dot 7H2O are isomorphs because their crystalline structure is the same. By crystalline structure, I would mean that in their crystal structure there are some water molecules present in their crystal structure. So same number of molecules are present, and also the same anion is also present. So their structure is quite pretty same in the crystalline structure. So they are isomorphs. So and this phenomenon is called as isomorphism. Again, the third is their electrical conductivity. Electrical conductivity of ionic compounds as such is very less. They are poor conductors. However, they are very good conductors in the molten state or in the when they are dissolved in water. They act as a very good conductor because when they are in molten state or when they are in gaseous state, when they are in the aqueous state, the compound breaks into the ions and the ions are free to move. Therefore, the electrical mobility of that aqueous solution increases and it conducts electricity. The next property of the ionic compound is about their solubility. The solubility of the ionic compound increases as a dielectric constant of the polar solvent increases. What do you mean by dielectric constant? Dielectric constant is something property of polar solvent in which there is a dipole moment, so it is according to that. So H2O or water has a dielectric constant of 80, C2H5OH has a dielectric constant of 27, and CH3OH has a dielectric constant of 35. So the ionic compound will be more soluble in H2O than in CH3OH and least soluble in C2H5OH. So more the dielectric constant of the polar solvent, more will be its solubility in it's there. Now, this was one of the factor determining the solubility of the ionic compound. The second factor which determines it that when it is dissolved in any solvent, there is some heat of hydration and there is a lattice enthalpy. Because it is in some forms mx solid, so we have to break it into m plus gaseous plus m plus x minus gaseous, and then there would be a heat of hydration for it which will turn into m plus aqueous and which will turn it into x plus x minus aqueous. So if the heat of hydration is large enough to exceed that lattice enthalpy, then its solubility increases. More would be the heat of hydration, the more would be the solubility, so to say, of that compound, that ionic compound. So let us take an example how to determine this solubility. So when we go down the group, because of the increase in the size, the lattice energy decreases because more compact the atom or molecule is, more would be its lattice energy. So as we go down the group, the lattice energy decreases, as well as the hydration energy decreases, because more the size, more or less would be the concentrated charge on it, and that's why its heat of hydration would also decrease down the group. However, when anion and cation that we are considering, if they are of comparable size, then this solubility is determined by the cation. For example, if it is something like BeOH whole twice, beryllium OH whole twice, then MgOH whole twice, calcium hydroxide, and let's say strontium hydroxide. So if we have to compare their solubility, we have to say that because cation and anion are normally pretty of comparable size, therefore whatever the ratio, whatever is determined by the cationic ion will determine its solubility. So when we go down the group, the lattice energy also decreases and the hydration energy also decreases, but the lattice energy decreases much faster than the heat of hydration. Therefore, the solubility of strontium OH whole twice is the greatest, then the CaOH whole twice, and then Mg, and the least soluble is beryllium hydroxide. So because down the group the lattice enthalpy decreases much more when as compared to the hydration energy when the anion and cation are that are in consideration having the same atomic radii are of comparable size. Now when the anion is pretty large as compared to that of the cation, let's say take an example of BeCO3, beryllium carbonate, magnesium carbonate, calcium carbonate and strontium carbonate. In that case, the lattice energy as we go down the group does not change pretty much, but the hydration energy still decreases. So in that case, the beryllium BeCO3 will have the more solubility as compared to MgCO3. MgCO3 in turn will have the more solubility from CaCO3, and which in turn will have the more solubility from SrCO3, because hydration energy for SrCO3 is the least, and the lattice enthalpy for the SrCO3 and all the other carbonates are pretty much the same. Therefore, the solubility that is in turn can be defined as determined by the delta H minus lattice enthalpy ratio. Delta H minus lattice enthalpy calculation, the more the negative quantity it is, or more it would be soluble, so it is most negative for BeCO3 than for MgCO3 than for CaCO3, and the least negative for SrCO3. That's why this is the trend for the cation and anion, in which they are in which the anion is much larger than the cation. However, if anion and cation are of comparable size, then the order is reversed. So we have studied about the how to calculate the ionic character in a covalent compound. Now we will study how to calculate covalent character, or how to predict the covalency of any ionic compound, how to compare two ionic compounds, the covalency of two ionic compounds. So this is determined by the Fajans rule, and before introducing the Fajans rule, I would like to introduce one term, which is polarization power or polarizing. So when cation, and this is cation and anion, when cation and anion approach each other to form an ionic compound, the cation polarizes, cation distort the electron cloud of the anion. It distorts the electron cloud of this anion. So this power of cation to distort the electron cloud of anion is known as its polarizing power, and it's known as the polarization. So more the polarization of anion, more would be the covalent character of the molecule. So more would be the covalent character of molecule. So the polarization, the factors on which the polarization depends are something like this. This is inversely proportional to the size of cation, because less would be the size of cation, more would be the concentrated charge on it, and it can distort the anion, or it can polarize the anion much more in that case. Therefore, polarization increases, polarization is inversely proportional to the size of cation. So, or so to say, it is size of the 1 size of cation is inversely proportional to the covalent character. So polarization is also directly proportional to the size of anion. So more the size of the anion, more would be the polarizing power. So for the size of cation, let's say if I take an example, BeCl2, MgCl2, CaCl2 and SrCl2, then you can say that because the Be is the smallest in size, therefore it would polarize the more. So covalent character of BeCl2 is greater than MgCl2, which in turn is greater than CaCl2, which in turn is greater than SrCl2. In this case, if we consider the compounds LiF, LiCl, LiBr and LiI, so more the size of the anion, more would be the polarization, more would be the covalent character. Therefore, the covalent character of Lii is greater than the covalent character of LiBr, which in turn is greater than the covalent character of LiCl, which in turn is greater than the covalent character of LiF. Now, again the polarization power is directly proportional to the size on the cation and also the size on the anion. So more the size, more the charge on the cation and more the charge on the anion, more would be the polarization. So let us take one example. If it is NaCl, MgCl2 and AlCl3, so Na has the positive charge 1, Mg has the positive charge 2 and Al has the positive charge 3. So more the charge on the cation, more would be the polarization and more would be the covalent character. Therefore, covalent character of AlCl3 is greater than the covalent character of MgCl2, which in turn is greater than the covalent character of NaCl. This was for the size of the cation. Charge on the cation. For the charge of the anion, the illustration would be, if you will consider AlF3, Al2O3 and Aln. The cation in all these three compounds is the same. There is a change in the anion. So the anion is charged in AlF3, it is charged -1, in this it is charged -2, and it is charged -3. So more the charge on the anion, more would be its polarization and more would be the covalent character. So Aln is more covalent than Al2O3, which in turn is more covalent than AlF3. So these are the four factors. Apart from these four factors, there is one more factor called the pseudo inert gas configuration, which also determines the, what you can say, the polarization power of the cation, and it is not asked in JEE till now, but it can be asked because it is not that trivial. So the fifth factor on which the covalent character in the ionic compound depends is that the pseudo inert gas configuration. So let us consider the Cu+. The Cu+ ions has a configuration of argon 18, 3d10. This is the configuration for the Cu+. So you can say that it has 3s is also occupied, 3p is also occupied, and 3d is also occupied, and the first and the second valence shell is also occupied. So it is something like all the orbitals which is occupying are completely filled and there is no vacant orbital present. So therefore it is a pseudo inert gas configuration. Let us consider the Na+. Na+ has an electronic configuration of 1s2, 2s2, 2p6. So it has an electronic configuration of neon. So it has the inert gas configuration, and this type of configuration is known as the pseudo inert gas configuration. So it is found that the pseudo inert gas configuration, the cation having the pseudo gas inert configuration, has more covalent character as compared to the cation having the inert gas configuration. So for example, if you will consider CuCl and NaCl, then CuCl will be more covalent in character as compared to NaCl. So when we are considering covalent character, CuCl is more covalent than the NaCl. So this is the term one different, I should say, the not usual factor on which this covalent character depends. So yeah, so let us see some application of that. Let us see if you are asked about the solubility, let's say Ag2s and AgO. If you are asked about the solubility, whether the Ag2s is more soluble or AgO, how will you predict? This can be done in some way, because we know that the S2- is larger in size as compared to O2-. So the polarization of the sulfur -2 anion is more than the polarization of the O2-. Therefore this is more covalent in character as compared to the AgO, and the covalent character are less soluble in the polar solvents. Therefore Ag2s is less soluble than AgO in water. So this is how we can comment on solubility based on the again one more thing is that the bigger anions are, there is a colored, the color of some compounds can be explained on the basis of polarization of these compounds, because as the bigger anions are there, their electrons are polarized and just some energy can be provided, and then can radiate a visible spectrum light. So the color in some of the compounds can be explained on that basis. Now the melting point can also be determined by using this covalent character criteria. Let's say if I take BeCl2, NgCl2, CaCl2 and SrCl2. So we know that since the anion is same, so we have to predict on the basis of the cation. More smaller the cation, more would be its covalent character, and more would be its covalent character, the less would be its melting point, because the melting point of ionic compound is greater than the melting point of covalent compounds. So this will be the trend that would be followed in this case. Okay. So this was all about the electrovalent bond. Now turning on to the second one, covalent bond. As you know that covalent bond is formed by the sharing of electron between the two atoms that are combining to form a molecule. So what do you mean by sharing of an electron? Let us see one example that how sharing is done in the chlorine molecule. So two chlorine atoms, so first we will draw the Lewis structure for the chlorine. So chlorine has 7 valence electrons, that is 3s2 3p5. So this is the Lewis dot structure for chlorine, and the other chlorine also comes in the picture. It also has 7 valence electrons. So to complete its octet, it needs one more electron, and this chlorine atom also needs one more electron. So it would be better if this electron, these two electrons can be shared by both this chlorine and this chlorine, then the octet of both will be complete. So this is what we call as sharing and the covalent bond formation. So it does something like this to chlorine, and there are two electrons, that is structure, and these two electrons belong to this chlorine atom also and this chlorine atom also. So this is the formation of the chlorine molecule, the Cl2 molecule. So this also has its octet completed, and this also has its octet completed, and this is the Lewis dot structure for chlorine. Yeah. So let us draw the structure, the Lewis dot structure for one or two more compounds, so that if it comes in the somewhere to choose out of 4 options to choose which one the Lewis dot structure is correct, you can predict. So let's say write of the CCl4. So CCl4, what would mean? The carbon, how many valence electrons carbon has? 4. So carbon is the central atom. So how do we decide central atom, or what is central atom? This is again an issue, and this will be discussed in the later part of this lecture. So this is C carbon, this is chlorine, let's say 4 chlorine are there. So this chlorine has 7 valence electrons, something like this. Now carbon has 4 valence electrons, so it shares each one of its electron with each of the chlorine atoms. So 2 are here, 2 are here, 2 are here, 2 are here. So I draw this ring which will show the octet completion of the carbon, and this ring I will draw to show the octet completion of the chlorine. So in this way, this is the CCl4 compound, CCl4, and this is the Lewis dot structure for the CCl4, and in this way you can see that octet of each atom is completed, and therefore this is the Lewis dot structure for CCl4. Yeah. So this was, I have taken this illustration, these two illustrations. In this only the single covalent bond is being formed. How to draw the Lewis dot structure when there are double covalent bond present, or triple covalent bond present. So let us take one example of each of the double bond and triple bond. So let's say the structure of CO2, that is the carbon dioxide. So carbon has 4 valence electrons and oxygen has 6 valence electrons. Oxygen has an electronic configuration of 1s2, 2s2, 2p4, and the carbon has an electronic configuration of 1s2, 2s2, 2p2. So oxygen has 6 valence electrons and carbon has 4 valence electrons. So it shares its 2 electrons with the carbon atom. So here there are 4 electrons, and it again shares its 2 electrons from here. So this is the octet completion for the carbon atom. It has 8 electrons in its octet is completed, it's 8 electron. This is the octet completion for the oxygen, and this is the octet completed for this oxygen. So this 4 electrons determine the double bond. If we want to remove, if we want to replace these bond by bonds, so it can be replaced something like this, that this has 2 bond formation, this is double bond, this is double bond, and these are the 2 lone pairs present on the oxygen molecule. So this is how to draw the what you can say, the Lewis dot structure for the compound which has the double bond in it. Let's say one example in which there is a triple bond, that is C2H2. Now there is a carbon, there is also a carbon, there is a hydrogen, and there is a hydrogen here. Now hydrogen has one volume, 1 electron, and it has 1 electron, so these both can share 1 electron with this. So here it is the 2 electron, and here it is 2 electrons. Now it has 3 valence electrons, if these both share, these will have 6 valence electrons shared, and these 2 and these 2 will combine to give them this 8 electrons and this 8 electrons. It is something like this, that it is 3 here. So this is the octet completion for this carbon. This is the octet completion for this carbon, and hydrogen will have the configuration of helium, and this hydrogen will have the configuration also of helium. So this is the compound of C2H2, in which you can see that triple bond is present, and this is how to draw the Lewis dot structure for the compound having a triple bond in it. So it can be also replaced with something like this, triple bond C, H and H. So this is how to draw if you want to replace it by bonds. Fine, and it has no carbon and no hydrogen has any lone pair on it. Yeah. So the next question is how to decide the central atom. The central atom in CO2, as you can see, is the carbon, and central atom here is also carbon. But how to determine the central atom is the issue which I am going to take first. There are few criteria on the basis of which we can describe what would be the central atom. In most of the cases, you can just look at the element and you can determine what should be the central atom, but there are some molecules in which it is difficult to identify what should be the central atom. So for deciding the central atom, the first thing is, in the most of the compounds, the least electronegative element is determined as the central atom. This is one of the property, that least electronegative element should be the central atom. A second one is that the atom which is present in the least number of amount, which is less in number I should say, can act as a central atom. This is the second criteria. The third criteria is that the central atom is the atom which has the maximum bonds present, which has the maximum number, which can form maximum number of bonds, or you can say which is quite equal to the number of valence electrons present in the atom, it is equal to. And the fourth criteria is the atom having the highest atomic number, or the highest atomic number or largest atom act as a central atom. So by these 4 criteria, if you are given a compound, you should apply, if you are given an H2O, then apply these 4 properties to hydrogen and these 4 properties to oxygen. The one which satisfies the most criteria should be the one which should be the act as the central atom. And by these 4 properties, it is quite sure that hydrogen and fluorine can never act as the central atom. This is the thing. Now after this, the next thing would be the coordinate bond, which I have explained in that thing when there is a vacant orbital or something like that present, you can do this. But this coordinate bond or dative bond is something like this: when the electron pair is shared, the electron pair of one element is taken into consideration, but it is shared by both the elements. For example, NH3, here it is ammonia, it has one lone pair in it, one lone pair. When another hydrogen ion comes, so it donates its lone pair to the hydronium ion, so it is act as a donor and this act as the acceptor, and the resulting would be the ammonium ion, which would be nitrogen linked to the 4 hydrogen and positive charge on it. So this would be the structure of the ammonium ion. So this is how this bond is known as the coordinate bond, through which the lone pair is connected to that of the hydronium ion. Also, one more example can be in the ozone. Ozone is O3. So ozone is, the structure of ozone is something like this, that it has this structure, it has 2 electrons, 2 lone pairs, and 1 oxygen is present here also, and this donate its lone pair into the vacant orbital of oxygen. So because oxygen has 1s2, 2s2, 2p, 1s2, 2s2, 2p4, so it has one vacant orbital which can, if energy is provided, it can become vacant, because this is something like this. So if energy is provided and it can be paired, then it has one vacant orbital. So this oxygen donates its lone pair to this oxygen. So this oxygen, which has originally 2 lone pairs, has now 3 lone pairs, and this oxygen atom only has 2 lone pairs. Sometimes it happens that this coordinate bond is replaced by the positive on the which is donating donor, and the negative sign on the acceptor. So in that case, when we replace it by the positive charge comes to nitrogen, and when you replace the negative on the hydrogen, it cancels the positive charge which was originally on hydrogen, and it comes as neutral. So if you want to replace in ozone the coordinate bond by the covalent bond and the positive and negative charge, you can do, so the structure would be something like this. There will be ozone, this would be double bond, this will have no effect. This will be single covalent bond replaced by single covalent bond. This will again have this will have negative charge, and this will have the positive charge. This will be the structure of ozone in that case. So this is how the coordinate bond can be replaced by a single covalent bond and replaced by the positive and the negative charge. Yeah. So next thing, or the next, is the formal charge. Formal charge, because you know that when the electronegativity of the combining elements are different, there is always the shifting of positive and negative charge based on the electronegativity. So there is some formal charge developed in that. However, formal charge does not, there is a question that formal charge do not indicate the real charges, but it helps us determine that which of the Lewis structure as the most stable. So for example, if I have to determine the formal charge on oxygen, let's say ozone, so we know the ozone has a Lewis structure of this, that it has 4 and this has 6 electrons. So I want to determine the formal charge on this oxygen, this oxygen, this oxygen also. So the formal charge is defined as the total number of valence electrons present in the free state, minus total number of non-bonding electrons, or I should say the total number of lone pair, minus half times total number of bonding electrons. So bonding electrons, I replace it by B. So this would be the formal charge on that atom. So let's name it 1, this is 2, and this is 3. So the formal charge on the 1 would be is equals to total number of valence electrons in the free state on this oxygen would be 6, minus total number of lone pairs. How many lone pairs are there? There are 4 lone pairs, minus half time total number of bonding electrons. These are, so every single covalent bond can be replaced by 2 bonding electrons, so it constitutes 4. So it is 6 minus 4 minus 2, which is equals to 0. So it has this first oxygen has the formal charge 0. Now consider the second oxygen charge. Second would have again the total number of valence electrons would be 6, minus the lone pair are 2, minus half times there are 6, 2 and here 6, so there are 6 bonding electrons. So in this case this would be equals to plus 1. For the third oxygen it would be equals to 6 minus there are 6 in fact the lone pair, minus half time only 2 bonding electrons are there, so it has charge minus 1. So this should be replaced by plus and this should be replaced by minus, which is true as we have done in the coordinate bond also. So this is how the formal charge is calculated for any compound. So if any compound is given to you and you were asked about the formal charge, you have to use the formula that total number of valence electrons in the free atom in the free state minus the total number of lone pair present on the atom and minus half into total number of bonding electrons. This is how you can calculate the formal charge. Now we are talking about the octet rule from quite a long. So there are also some limitations of octet rule, because octet rule is not pretty clear because there are some elements in which the octet rule does not follow. For example, there are some element in which there are the incomplete octet of the central atom. For example, if I take the VCl3, example of VCl3, this is Cl, Cl, Cl. So Lewis dot structure, boron has three valence electrons, and so chlorine, this is 2, this is 2, this is 2, this is 2. So this has its octet complete, this has its octet complete, this has its octet complete, but this only has 6 electrons and it is found to be stable. So incomplete octet of the central atom in this case, therefore it's not followed, the octet rule is not followed. So it generally happens in which there are less than 4 valence electrons. In those species the octet rule is quite not followed. The second would be the odd electron molecules. Odd electron molecules would be the number of electrons, the total number of electrons in that molecule would be the odd number. In that case the octet rule is not followed. For example, there is NO. So N has the electrons, 7 electrons, and oxygen has how many electrons? 8 electrons. It has 15 electrons. So this is oxygen and this has this and this has this. So this is the structure would be something like this, and there would be 1 electron present more from here. So in this case the octet rule is not followed because octet of the oxygen is complete, however its octet, the octet of nitrogen, is not complete. So in this case the octet rule is not followed. One more odd electron species is the NO2, in which the structure is something like this, the NO2, and you can draw here from here and from here. So in this case also the octet is not complete for each of the electrons. So these are the odd electron species. Now for some there is an expanded octet, because here it is the deficiency or incomplete octet, and there are some molecules in which they are expanded octet because of the presence of the 3d vacant orbital. For example, in the third period, in the phosphorus, in the sulfur, we are not taking into consideration the 3d vacant. There is a vacant 3d orbital which has not been occupied. Because of that there can be more than 8, there can be a combination of more than 8 electrons, and the octet rule is not satisfied in those cases. For example, I will take into account a compound called phosphorus pentafluoride, PF5. If you look into the PF5, it is something like this, that it is surrounded by F here, F here, F here, 3 in the equatorial position and 2 on the axial position. So this type of bond is formed, and these 3 are planar, and this is axial and this is axial. So octet of each of the fluorine is complete, however the phosphorus has an expanded octet because it has 10, 2, 2, 2, 2, 2, it has 10 electrons in its vacant orbital. So the expanded octet is expanded. One more example is of SF6, in which it is bonded with 6 fluorine atom. Yeah, so 12 electrons around the S atom. One more drawback or other drawbacks of the octet theory would be that it doesn't account for the shape of the molecules. You can't comment on the shape of the molecules. You can't determine what would be the shape of SF6 or what would be the shape of the PF5. This cannot be determined again, and it is based on the inertness of the noble gases, that the noble gas does not react, therefore they achieve the octet configuration. The whole octet theory is based on this fact. However, it is known, or it is found, that there are some compounds called XCF2 or XCOF4, KRF2. So the krypton or xenon also reacts with oxygen and fluorine, so they are not completely unreactive. So this was also one of the drawback of the octet theory. And one thing is that it does not comment about the energy of the molecule, that what would be the energy of the molecule after combining, or how to predict the energy of the molecule. So these are some limitations of the octet theory. Because of this, the new theories have been modelized, and the first one is the valence bond theory. So the valence bond theory completely depends on the atomic orbitals, a new term called atomic orbitals, overlapping of atomic orbitals, the principle of hybridization, superposition, which we will learn in this lecture now. Discussing lecture now. So the next topic would be the valence bond theory. So what does valence bond theory say? Let's say there are two. Let us take an example of hydrogen atom. One hydrogen atom is here and one hydrogen atom is here. Initially they are separated by infinite distance. They are very far away. So when they are approaching each other, so what are the forces which are taking place? One is the nuclei of hydrogen atom is attracting the electron of other hydrogen atom. This nuclei of hydrogen atom is also attracting the electron of other hydrogen atom, and these two electrons of hydrogen atom are repulsing each other. So there are two opposing forces. One is attractive force and the other is repulsive force. So when they are approaching each other, there is a condition. A condition comes after which the energy decreases, and then it is again increasing. So the point where the minima is obtained is what we have defined as the bond energy of the hydrogen molecule. So a graph can be plotted between the energy of the molecule and the distance, internuclear distance. So let's say this is energy, we plotted here, and this is the internuclear distance, and this is, let's say, the line for the 0. So when they are infinite, at the infinite distance, it would tend to be 0. Now when they are approaching each other, the attractive forces are dominant over the repulsive forces, the energy will decrease, and at the certain moment the repulsive forces will now, as they are coming more closer, the repulsive forces will dominate the attractive forces now, and the energy will now increase. So this point, this minima will determine the bond energy of the hydrogen molecule, and this distance would be the bond length of the hydrogen molecule. So for here, let's say it has the two molecules are separated by this, then here they are a partial overlap, and this here is this overlap. So this distance would be the bond length, and this would be the bond energy of the hydrogen molecule. This is how we determine it. So the next thing in this would be that this is the valence bond theory, and this is how we determine this for this. But when they are approaching each other, the attraction forces are dominant over the repulsive forces. So there is a partial, you can say, the interpenetration of the two atomic nuclei. So finally something like this is obtained. So this is the orbital overlapping concept which takes place when two hydrogen or any two atoms are approaching to form a covalent bond. What do you mean by overlapping of atomic orbitals? We know that there are atomic orbitals S, P, D and F. There are three types of p orbitals also, px, py, pz, according to their nuclear orientation. So first there is a positive overlap also, there is a negative overlap, and there is a zero overlap also. So I will determine how the positive overlap is defined, how the negative overlap is defined, and how the zero overlap is defined. So for example, this is a S orbital which is spherical in shape. So this is a S orbital and it has a positive charge on it. Fine. This is a p orbital which is a positive charge, and this is a negative charge. Fine. So if it is approaching from here, let's say this axis would be the x, so it would be the px. So when these two would be approaching each other, then there will be positive overlap because the positive lobe is overlapping with the positive lobe. So in this case, the lap will be positive. So if we are considering, this is one of the case for the positive overlap. Another can be, this is the head-on overlap, by the way. So this is minus plus, this is minus plus, and there is another p orbital. This is plus, this is minus. So let's say the axis of this would be x, and this axis would also be x. So this would be px, and this would be px. So this orbital, this overlapping is also head-on, and this is positive because positive is overlapping with positive. So this overlap is also positive. Another case of positive overlap could be simply if there is a plus of s orbital and there is another plus of s orbital. So these two orbitals are also overlapping to form a positive overlap. Now, this was also all in the terms of what you can say is the head-on overlap. Now there is also a thing called side-on overlap or sideways overlapping, which takes place in case of p orbitals or d orbitals also. So there is a p orbital plus minus and another p orbital plus minus, and let's say this axis is z, so it can be px py both. Let's term is px and this is also px. So this is also overlapping positively, this is also overlapping, result is positive. So ultimately this is a positive overlap. So these are the few examples for the positive overlap. Now let us take some example of the negative overlap. So negative overlap can be something like this. If this is positive and the p which is approaching is negative here and positive here, this is an example of negative overlap. However, this is never achieved, this condition is never achieved because positive and negative cannot overlap. But to show that, I am also showing that it will be a negative overlap, that is, it will not be a favorable condition. Positive overlap indicates that it is a favorable condition for that overlap to be formed. Negative overlap would say that the overlap will not take place. For the p orbital also, if we say this is negative, this is positive, and this is negative, this is positive, so this would also be a negative overlap in that case. For this case, if you will sideways, if you want to do it, just replace this by minus and this by plus. This is again both here sideways overlapping is minus, and this is also the negative overlap. So this is the example. These are the examples of negative overlap. Now there can be zero overlap also. How the zero overlap is possible? So something like this is possible, that this is positive negative and there is the s orbital which have the positive. So the amount of positive that is overlapping with this plus is cancelled by this plus minus. So this is said that the s orbital can never participate in the sideways overlapping. There is always the head-on overlapping as far as the s orbital is concerned. So this will have the zero overlap. So zero overlap is also possible for two p orbitals. If this is the, let's say, z axis and this is px and this is py, these two will not overlap because the orientation of both the orbitals should be same. So this is also an example of zero overlap. So based on this positive overlap, if positive overlap determines that the positive overlaps determine the favorable condition for the for the covalent bond formation, and the negative overlap determines that the covalent bond formation is not feasible or is not possible. Now based on this overlapping, there are the two types of bonds, sigma bond and pi bond. The first is the sigma bond and the second is the pi bond. So sigma bond is always formed by head-on overlapping. So I showed you some example that one case could be like this, plus between the s and p, one could be between the s and s, and one could be between the you can say between the p and p. So this is plus, this is minus, this. So these three are the examples of the sigma bond formation in which the head-on overlapping is being taking place. For the pi bond formation, there should always be a sideways overlapping with something like this, that this is plus, minus. Sideways overlapping can also be done with the d orbital. Let's say this is the orbital which is under consideration. So this can interact. If this is plus, minus, plus. So sorry, minus. So this is also a sideways overlapping. This is dx square minus y square, and this is px or py or pz, whatever you want to say. So this is also how the sideways overlapping the pi bond can be formed. So these are the few examples in which the pi bond overlapping can be formed. So this can also be represented as something like this, that there is something called this, and there is another shape of a saucer, I should say, and this is the nuclear axis. So this is how we can determine that it is a positive density, it is a negative density, and you can show it something like this. So now I will turn to the VSEPR theory, that is the valence shell electron pair theory, which will determine the number of lone pairs, how to determine the number of lone pairs and the number of bond pair, and also the very important concept in the chemical bonding. And a lot of questions have been asked on this concept, which is known as hybridization, that you are given a molecule and you have to predict its hybridization, and it is a very common concept on which many questions have been asked in the previous years. So let us start with VSE PR theory. So some of the postulates of VSE PR theory is the shape of the molecule depends upon the number of valence shell electrons. So bonded or non-bonded, that is bonded, by bonded we mean bond pair. Bonded electrons will mean the bonding electron that participate in the covalent bond formation, and by non-bonding electron it would mean the lone pair. So it says that the shape of the molecule is determined by both the bonding and the non-bonding electron. The earlier Lewis dot structure, which we are saying, was not able to predict the shape of the molecules. This was the first postulate, that bonding and non-bonding together contributes to the shape of the molecule. The second is that these bonding electrons and non-bonding electrons aligns in such a way that to minimize repulsion and to maximize the distance between the electron pairs. So these align themselves in such a way, and the geometry is determined by that. So the repulsive interaction between would be the lone pair repulsion is greater than the bond pair repulsion, and which is greater than the bond pair repulsion. My bad, sorry, it is bond pair, not bone pair. So lone pair repulsion is greater than the lone pair bond pair repulsion, and which in turn is greater than the bond pair repulsion. Why is it so? Because the lone pair is completely localized on one atom. This is localized, but as far as bond pair electrons are considered, they are shared between the two atoms, so they are delocalized between the two atoms. So it is not as concentrated as compared to lone pair. So lone pair will have the more repulsion as compared to lone pair bond pair, and which is in turn is greater than the bond pair. So whenever you have to predict the geometry where to place the lone pair, you first have to consider that how many lone pair repulsion are coming into effect and what is the angle. So the symmetry or the size, the geometry in which the lone pair repulsion would be minimum would be the stable configuration for that element. Now that lone pair repulsion also distorts the geometry of the molecule. So if there can be two cases, either there are no lone pair or there can be lone pair. So in case of the no lone pair condition, it is perfect geometry, what you can say, but in case of the lone pair, if there are present some lone pair, there is some distortion of the geometry. So let us first see the shape of the molecules in which there is no lone pair present. So let's say number of electron pairs. I will make a table in which there are number of electron pairs and the molecular geometry and shape, so to say. So if the number of electron pairs are 2, that is there are 2 atoms, then the molecular geometry would be something like this, that is AB2, B, and it would be a linear unity. So in this case, remind you that we are not considering any lone pair. The lone pair on the central atom considered is 0. In that case, it would be linear and it would be something like AB2. If there are 3 number of electron pair, then it would be something like A would be here, B would be here, B would be here, and B would be here. So it will something like the trigonal planar shape, because this is a planar geometry, this is a planar shape, all these 4 molecules are in the same plane. If there are 4 molecules, then it would be something like this. B would be here, B would be here, and B would be here, and it would be tetrahedral in shape, so to say. So it is tetrahedral, and the angle between this is, you can say, is 180 degree. The angle here is 120 degree, and the angle here is 109 degree. 109.5 to be exact, but 109 degree. So in the other case, if there are number of electrons are 5, the molecular geometry would be something like this, that A, B, the geometry of that PA5 which I have drawn earlier is something like this. B, these 3 these three are in plane and these are said to be in equatorial plane. So to say, these three are to be said in, let us draw with the different colors so it will be quite visible to you in that case that how are we drawing it. So these three are in the same plane and this plane is known as the equatorial plane, and these two elements are said to be in the axial plane. And the geometry, this geometry is known as the trigonal bipyramidal. I will not write that. This geometry, this shape is said to be trigonal bipyramidal. The other one is if there are number of electron pair are 6, then it would be the octahedral in shape, that is it would be A here and B and B, and there would be 4 in here, something like this, and this would be in the same plane. These four B orbitals will be in the same plane. So in here also this angle which we are considering would be the 90-degree angle, and this angle you are saying would be is equals to 120-degree angle. And in this all angles, this angle is also 90 and this angle is also 90 degree. It is an octahedral geometry and the shape would be octahedral also. So now let me give you an example of each of these shape. So for AB2 you can have the example of BeCl2. This has the linear molecular shape is linear, but it is in the gaseous form. Now why I am stating it as gaseous, you will look at it in the later part of the chapter. For the AB3, there is BF3, you can say, or BCl3 is the example. For AB4, you can have CCl4, which has the tetrahedral geometry. For that AB5, I have shown you that is PCl5 was, or PF5 you can say. PF5 is not exist, sorry, PCl5. And for the 6, there is a SF6. So these are the shape, these are the geometry, these are some examples which have this geometry. However, in all these examples or on this geometry, these are the perfect geometry because I have not considered any of the lone pair. So what happens if there is a lone pair present on the central atom? In that case, the geometry, so to say, would be little bit distorted because there is an repulsion between the lone pair and the bond pair, or if there are more than one lone pair present on the central atom, then it will also have the lone pair repulsion, due to which there is not perfect geometry, there is some distortion in the geometry and the shape also changes. So now I am taking the case in which there are lone pair present. So let's say molecule type. Here I should write the molecule type. Here I will write the number of bonding pair electron. So if there are 4 bonding electron present, then definitely there will be 2 bond pair. Then here would be the lone pair. Here would be the arrangement, or to say geometry. Here would be the shape, and here I would give you some example. So let's start with the molecule type. So first molecule type is AB2E, that is there are 2 bond pair and 1 lone pair. In this case, the arrangement would be something like this, that A, B, B, and E is representing that electron pair, or so to say the lone pair. So lone pair will represent something like this. In this case, the shape will be bent. If there is another bond present B, it was trigonal planar. But when one lone pair comes, there is some repulsion in this. Because of this, it becomes a little bit bent. And example of this can be SO2. SO2 can be an example. I am showing here the single covalent bond, but it can be double covalent bond also, that doesn't matter. But the geometry would be one of the example would be the SO2. Second can be the AB3E, that is 3 bond pair and 1 lone pair. In that case, it would be something like A, B, 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 and 1 lone pair present. So this lone pair is having the lone pair bond pair repulsion from three lone pair bond pair repulsions are present in here. So it would be trigonal pyramidal. In the original case, or in the perfect case, it would be tetrahedral, but here it is trigonal pyramidal, and the example would be the ammonia, in which there is 1 lone pair and 3 bond pair. So next example is AB2E2, that is 2 bond pair and 2 lone pair, that is something like A, B, B, and here it is 1 lone pair and here it is 1 lone pair. So in this case there is also lone pair, apart from the lone pair bond pair repulsion, there is lone pair repulsion also. So its shape would be, you can say, bent, and the example is easy. It's water is a perfect example for the AB2E2 type of molecule type. If there is AB3E2, that is there are 3 bond pair and 2 lone pair, then what would be the geometry? In that case, the lone pair will occupy the equatorial position and not the axial position. Why is this happen? Is because the lone pair tend to occupy the position which are the less electronegative. So the equatorial position, in this case, in the case of the geometry trigonal bipyramidal, the equatorial positions are less electronegative as compared to the axial position. Therefore the electron tend to reside at the equatorial position. So this would be the geometry for AB3E2, and it is T shape, so to say, because you can say that it is something like this, bend it because of this repulsion, it bends a little bit, and this form at T, therefore it is written as the T shape, and the example for it this is ClF3. So in the ClF3, chlorine is the central atom, there are 3 fluorine atom, and because 7, so 3 valence electrons of chlorine are being shared with each of the fluorine atom, and there are 2 lone pair present. So this is for the C. The next one would be the AB4E, in which there are 4 bond pair, 1 lone pair. So its geometry, I will draw something here. So its geometry would be something like A. B4 would mean that 1 electron pair would be here, 1 would be here, 1 would be here, 1 would be here, 1 would be here. So this would be AB4, and the example is SF4. So I explained you the example. So here, why does it reside at the equatorial and not at the axial? One case was definitely the electronegative, and another case would be that if it would have reside at the axial position, there would be 3 bond pair lone pair repulsion at 90 degree. But if it reside here, there are only 2 bond pair lone pair repulsion at 90 degree, and there are 2 bond pair lone pair repulsion at 120 degree. So in this geometry there are less number of bond pair lone pair repulsion, and we know that the bond pair repulsion is greater than the bond pair lone pair repulsion. Therefore the first lone pair should appear at the equatorial position. Same for the second lone pair. The second lone pair position, if it is occupied at the axial position, so to say, if I place the second lone pair at the axial position, then there would be the lone pair repulsion would be at the angle of 90 degree. But if I place it in an equatorial position, the lone pair repulsion would be at the much greater angle, that is the 120 degree. That's why the second lone pair is also placed at equatorial position. So these are some of the geometries. So one molecule type still remains, so I will quickly draw it also. And for timing, that was it has the shape seesaw. The shape of it is said to be seesaw. One more example is AB4 E2. So it has 4 bond pair and 2 lone pair. So it is something like this: A, B, 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 and the 2 lone pair are here. So in that case, all the are equal because all are at the 90 degrees. So you can play the first lone pair at any place, but corresponding to this, the second should be placed at here because the lone pair repulsion would be at the 180 degrees. So this is the square planar geometry, a square planar shape, so to say. If there would be no 2 bond pair in place of this 2 lone pair, it would be square pyramidal, but here it is a square planar, and one of the example for this is XeF4. XeF4 would be the one of the examples. Yeah. And one more thing is AB5E. In that case, there would be bond pair here and 1 lone pair, and that electronic geometry is said to be square pyramidal. If they both are present, then it's square bipyramidal. If one bond pair and one lone pair present, it is said to be square pyramidal, and if two lone pair present, it is square planar, because all these four elements can now be said to be in the plane. So this was different molecule types having a different number of lone pair and bond pairs. So how it is distorted, the geometry and shape are distorted is being shown, and examples are also being given. So I will draw some of the structures to give you a little bit of insight into how to draw these structures. Many questions have been asked on the structure, on the basis of structure, and on this hybridization, so it's quite important that you learn this quite well. So yeah, let's take the example of SO2. How to draw the structure of SO2. So SO2 is something like this. So SO2, if you want to draw its Lewis George structure, it would be something like this, that here is an oxygen, here is an oxygen, it has two lone pair here, it has two lone pair here, it shared its two lone pair with sulfur, it shared its two lone pair with sulfur. So it has octet completed from here, it has octet complete from here, it has octet complete from here, and it has one lone pair. So it will be something like that. So it is a molecule type of form AB2E, one lone pair and two bond pairs. So it will be something like this, that oxygen, oxygen, and there is a lone pair. So ideally this angle should be 120 degree, but because of this lone pair bond pair repulsion, this angle would be less than 120 degree, because it is bent, it is not completely, you can say, trigonal planar, and it is found to be, the angle found experimentally found to be 119.5 degree, which reduces it. Now another example can be of NH3, which I said earlier. NH3, it has three bond pair or one lone pair, that is, it is a molecule of type AB3E. So it has one lone pair, so there are three bond pair lone pair repulsion. So this repulsion comes into account and reduces this angle to 107 degree from 109.5 degree. So if there is a question on how this angle, to explain this reduction in this angle, your answer should be the lone pair, because of that lone pair bond pair repulsion. So next would be in the H2O, which was of the form AB2E2, because it had two lone pair and two bond pair. So there are two lone pair and two bond pair, so there is some repulsion here also and some repulsion here also. So its angle from 109.5 gets reduced to 104 degrees. It is reduction of 5.5 degree, and this is how we can explain. There is more reduction here because there are two lone pair present, and lone pair repulsion is greater than the lone pair bond pair repulsion. Therefore the angle decreases to much greater amount as compared to NH3. The next is the SF4, which is of the form AB4E. So F would be here, F would be here, F would be here, or I should say F would be here, and lone pair should be here, lone pair, and F would be here. This is one of the possibility. One of the possibilities also that F would be here, F would be here, and another F would be here, and lone pair is placed here, and F would be here. Now in this case there are three lone pair bond pair repulsion at 90 degree. This is also 90, this is also 90, and this is also 90. So three lone pair bond pair repulsion at 90 degree. However, in this case there are only two lone pair bond pair repulsion at 90 degree, and we know that the bond pair repulsion is greater than the lone pair bond pair repulsion, is less than the bond pair lone pair repulsion. So we want to minimize the lone pair bond pair repulsion. Therefore this is the correct structure, that is the, I should say, the seesaw structure of the type molecule type AB4E, seesaw structure in the shape, and this is the correct thing. Yeah, it would be more stable. So same for the AB4E2, which I have explained earlier, that if you have the ClF3, let's say, so the second also should come here, because if it comes here, the second lone pair comes here, they both are at the angle of 90 degree, but if it comes in the equatorial position, they are at the 120 separated at a larger angle, so it should come at the equatorial position. So correct formula, the correct structure for ClF3 would be this, the two lone pair are present here, and F, and not this, or something like this, that one is here, one is here, one is here, one is here, one. So this is the wrong, and this is the correct structure. In this there are more, this is more stable because of the larger angle difference, 120 degree, so to say, or it would be greater than 120 degree in fact, because this lone pair repulsion will cause to expand it a little bit, so it would be greater than 120 degree. And it has the T shape, you can say. The AB4E has the seesaw shape, and the AB3E2, 2 lone pair and 3 bond pair, has T-shaped structure. So we are able to predict the geometry through the VSEPR theory. So this is one of the merits of the VSEPR theory. The next topic, and the very important topic, is the hybridization. Many questions have been asked on this concept in the chemical bonding from hybridization, so it's quite important that you understand this concept quickly. So I will explain you about the hybridization. Hybridization is, first of all, is a hypothetical concept, because when we are looking for some structures that the energy of orbitals was found to be same. However, it should not be same, because the s orbital energy is different from that of the p orbital energy. But when they are experimentally deduced that the orbitals energy are coming to be same, so hybridization is an hypothetical concept according to which, let's say, if there is one s electron and 3p electron, one s orbital, or I should say one s orbital and 3 p orbitals, then these combine together to form 4 sp3 orbitals, one part of s and 3 part of s, 4 sp3 orbitals, which are equal in energy, whose energy, all the 4 orbitals have the same energy. The number of orbitals would be equal to s plus p, number of orbitals would be generated, and these hybrid orbitals will be oriented in space to obtain the most minimize the repulsion and obtain the most stable geometry. Now, what are the important conditions for hybridization? The orbitals which are undergoing hybridization should not have much difference in their energy, because if there is much difference in energy, their hybridization cannot take place. And that it is the orbital that undergo hybridization and not the electrons. That is, you will not say that it has 2 electrons and it has 6 electrons, so 8 electrons undergo hybridization. It would be that 1s and 3p electrons are undergoing hybridization and producing 4 sp3 orbitals. So first important number is that steric number. Steric number is the number which determines what would be the hybridization of the element. Steric number is defined as the number of bond pair plus the number of lone pairs. This is the steric number. Number of bond pair would mean the pair of bond pair, number of bond pairs, sorry, the number of atom bonded with the atom, or number of bond pairs, plus number of the number of atoms bonded with central atom plus number of lone pair. This will determine the steric number, and this rule is given by the Gillespie. First of all, this rule is not applicable to the odd electron atom and something called definition atom B2H6, something like this, because this has 3 center 2 electron bond, 3 center 2 electron bond, which we will study later in this lecture. So for example, steric number for, let's say, CO2, number of atoms bonded would be 2 plus number of lone pairs on carbon is 0, so its steric number is 2. Steric number is 2. For example, if you are consider the SO2, for example SO2, then the number of atom bonded is 2, number of lone pair would be 1 lone pair would be present on this, so the steric number is 3. For example, ClO3 minus, the number of atom bonded are 3 and the number of lone pair is 1, so steric number is 4. So this is the steric number which will determine what would be the hybridization of the element. If the steric number is 2, the hybridization would be sp. If the steric number is 2, I am writing here the hybridization, or I think I should make a separate table because it is very important. The table is important, understand? So yeah, so here it is a steric number, there it is a hybridization, and here it is geometry. So if steric number is 2, the hybridization would be sp and geometry would be linear, if steric number is 3, the hybridization would be sp2 and the geometry would be trigonal planar. I think I should not write that trigonal planar. The hybridization, if the steric number is 4, the hybridization would be sp3 and geometry would be tetrahedral. If the steric number is 5, the hybridization would be sp3d, and the d involved here is dz square. This is important because it can be asked as an objective question that which d orbital, specifically which d orbital is involved in this hybridization where the steric number is 5. So it is dz square, and geometry in that case would be trigonal bipyramidal. If the steric number is 6, the hybridization is sp3d2, and the orbital which are involved in this are the dz square and dx square minus y square. So this is also you have to keep in mind, sp3d2, and the geometry in that case would be square bipyramidal, and if it is 7, it would be sp3d3, and in this case the d orbital involves are dxy, dyz and dxz. So completely different from the orbitals, d orbitals which are involved in the 6, and the geometry in this case would be pentagonal bipyramidal. Yeah. So now we will talk about the individual hybridization, that what would be the hybridization. First we will talk about the sp, then sp2, and I will take some examples on each of these to explain how the hybridization is taking place. So let us first start with sp hybridization. So sp hybridization, as I said, has the steric number of 2. An example, what would happen in this case? Let's say I will explain it by taking an example of BeCl2, that one s orbital and one p orbital, or I should say of the same valence shell, combines to form the two sp orbitals, which the sp orbitals has 50% s character and 50% p character. So in the example of BeCl2, we know its configuration is 1s2 2s2. So all the p orbitals are vacant. So in the excited state, one of the s electron is passed to one of the p electrons, and then these two 1 and s and 1 p electrons gets hybridized to form the two sp orbitals, which would be something like this, you can say, and a small one, minus minus plus plus, something like this would be formed according to the z axis, and this would be the 180 degree. This would be the sp hybridized element form, sp hybrid orbital that would be formed. Now when two Cl atom approach this, so it would be something like this, that this is this here and this here, and the two Cl atom also have the p orbitals there overlapping with this. So it would be, I would say, plus, it would be plus, it is minus minus, plus plus minus plus or minus. This is of the Cl atom, this is of Cl, and this is the B. So this is sp hybrid orbital, this is pure p orbital, and this is pure p orbital, and this hybridization of the middle beryllium is sp hybrid, and the shape, or I should say the shape would be linear in shape. It is in the same plane. Okay, so next is the sp2 hybridization. In that case, one s orbital and two p orbitals go under hybridization and produce three equally energized sp2 hybrid orbitals. So sp2 hybrid orbital will have 33.33 s character and 66.66 p character. So I have told you in that the basic model of periodicity, according that the electronegativity is also dependent on the s character. So here the s character is being decreased. So as the s character is being decreased, the electronegativity of the orbital is also being decreased. So you can say the electronegativity of sp would be greater than the electronegativity of sp2 hybrid orbital would be greater than the sp3, and so on. So as the percentage of the s character decreases, the electronegativity also decreases. Fine. So sp2 hybrid orbital, so there is, you can say, one s orbital and three p orbitals, something like this, and something like this, and this four orbitals when go under the overlap produce, so this is sp2, I have to draw only 2, I have drawn 3, so it is only 2, so produce something like this shape of this shape. So it is plus plus along this axis, along this axis, and this angle is 120 degree. This is difference in axis is 120 degree, and now this can undergo hybridization, that is BCl3 and go under hybridization, and all the forms formed would be through the head-on overlapping, that is sigma bond will be formed in this case. Next would be the sp3 hybridization. sp3 hybridization, I have told you earlier that 1s orbital and 3 p orbitals undergo the hybridization. So in this there is 25 s character, 4 equally energized sp3 orbitals are obtained, and example of sp3 hybridization are the CCl4 in which there is no lone pair, NS3 which has one lone pair, and the S2 has two lone pairs. So ideally after the ideally the sp3 hybridized orbital would look something like this, that is that of the shape of the tetrahedron, and this angle, this axis, this axis, this axis, and this axis, this angle should ideally be 109.5 degree. So this is the hybridized orbital, that is sp3 hybrid orbital should be something like this. And also in the NS3 and S2O, all the bonds formed are sigma bond, no pi bond is formed in that case also. Some more examples of sp3 hybrid orbital would be BeCl2. You will say the BeCl2 is linear, but I would say the BeCl2, I have mentioned earlier that it would be in the gaseous state, and I told you that why I am mentioning it gaseous would I discuss in the lecture. I will explain it in the lecture later in the lecture. So here I am mentioning the BeCl2 in the solid form. So what happens in the solid form, that BeCl2 has vacant p orbital. After undergoing hybridization, you can say in gaseous form 1s and 1p undergo hybridization, but still there are two p vacant orbitals. So what does this? This is Be, this is Cl, and this is Cl, or I should say this is Be, this is Cl, and this is Cl. So it is a lattice, it forms a lattice because Cl has a lone pair. So here comes the Cl, it belongs to the different Be beryllium atom, and the chain undergoes. So lone pair comes from here, and this donates its lone pair to another Be atom. This is another Cl atom which attached to this. This donates its lone pair to this beryllium atom. So each beryllium atom, and this is again, this chain is repeated simultaneous times, and this is in the solid form. You can say in the solid form the structure of BeCl2 is something like this. So each beryllium atom is joined to 4 chlorine atom, therefore its hybridization is sp3 because it has 4 bond pair and no lone pair, so it is perfect tetrahedron. Fine. Now BF4 minus. Again the boron, when you consider the BF3, only there is one p orbital vacant present here. So BF3, it is perfectly trigonal planar, and it again I remind you, it doesn't satisfy that octet rule, one of the limitations. So this is the BF3, but it has a vacant p orbital. So another F minus can come and donate its electron to that vacant p orbital. So the structure would be the complete tetrahedron in that case, or I should say tetrahedral. It would be something like BF4, and this minus charge would be on the boron now, but it is shown on the molecule also. So its molecule BF4 would be something like this, and it should be tetrahedron also. So for the carbon, we know that there are CCl4. For the silicon, there are SiCl4, and I have done hydrolysis on SiCl4 earlier in this lecture, in which we are formed that attacked in hydrolysis. When we are doing that hydrolysis, it was replaced by an oxygen atom, and HCl was produced. So these are the concepts you have to just, I am memorizing you that I have told it earlier. So now, for the, let's say, for the hydrogen would be N2H4. So there is one nitrogen atom, there is a hydrogen atom, this is a hydrogen atom, and there is again a nitrogen atom, this is a hydrogen atom, this is a hydrogen atom. This is connected from here, this is one lone pair, this is one lone pair. So it has the three bond pair and one lone pair each nitrogen atom. So this is a central atom. You can apply that 4 rules, and obviously hydrogen cannot be a central atom. I said you hydrogen and fluorine can never be a central atom, so central atom should be nitrogen. Nitrogen has an hybridization of sp3. So always the hybridization mentioned of a molecule is the hybridization of the central atom, because hydrogen definitely has some other hybridization, or in this case there is no hybridization of hydrogen, so to say, because there is only one electron. But the hybridization, when we say hybridization of a molecule, we are mentioning the hybridization of the central atom. So first you have to identify the central atom, and then you have to talk about its hybridization. So 3 bond pair and 1 lone pair, therefore the hybridization would be sp3. However, it would be a little bit bent because V-shaped, because it has not present of this. It is all N2H4 is also known as hydrazine. So if you are asked about the structure of hydrazine, it should be clicked to you in your mind that it is referring to N2H4. Yeah. Next important, or next peculiar structure is of the phosphorus, white phosphorus, so to say. Phosphorus is something like this. Phosphorus exists in the P4 structure. So P4 structure would be P is belonging to this P, and here this P. It is somewhat linked to this, and this is again, and this is again. So this is how the structure of phosphorus is. It is a very important structure. It has been asked sometimes that how, and this angle is 60 degree. It has been asked in JEE, I say 2007, that how many PP bond are there with an angle of 60 degree. So if you don't know the structure of the phosphorus, then you cannot comment on it. So this is an important structure, P4 structure, where the angles are at all these angles are 60 degree, and it has one lone pair, because there are 5 vacant 5 valence orbital, 5 valence electron for each phosphorus. So 3 are involved in bonding, and one lone pair is present on each. So its hybridization would be 3 plus 1 sp3, because 3 bond pair, 1 lone pair, 4 steric number refers to the sp3 hybridization. However, it will not be tetrahedral in geometry, because the lone pair will distort it. It is a little bit bent in shape. Yeah. So there are 6 pp bonds. You can say that there are 6 pp bonds. This is one. This bond represents that this is connected to this, and this is connected to this. And it is very strained molecule, because ideally it should be 109.5 degree, or so to say a little less than 109.5 degree, but it is restored to the 60 degree. So it has the, you can say, strain, or a strain angle of about 49.5 degrees. So it is a very chemically very reactive element, a very reactive molecule, P4 in structure. Another very interesting structure is of P4O6. These structures have been directly been asked in the JEE earlier in the 2000s, or in the 1995 when screen means were there. So P4O6, very important structure, or very popular structure, that is P O P O P O P O P. So you can see there is no PP bond in this P4O6. I have not drawn, I think I have drawn only 4. So 1 O would be something like this, and 1 O would be something like this. So this is the P4O6. So there is one question was asked in the JEE, that then which you have to say that following were the incorrect statement about the P4O6, and one statement was there is a PP bond in P4O6. So you have to tick that in that case. So it has also one electron, it has one lone pair, it has one lone pair. In this, the central atom is phosphorus. You have to first determine that the central atom, and it has 2 lone pair. Each oxygen has 2 lone pair. So this is the structure of P4O6. So 3 bond pair and 1 lone pair. That's why it has sp3 hybridization. Right? So these are some very peculiar examples of sp3. One more example is of P4O10. Very nice structure of P4O10. In this, what happens that the same as this POP, O, P, O, P, O, P. This is the same as this. There is also the same as this. But now, instead of that lone pair, there is a double bond oxygen with this. So you will say after the 3 electron atom, there is no vacant orbital left for the phosphorus. How will this form this double bond. This is because the phosphorus also has vacant 3d orbital. So this is formed via back bonding, I should say. The oxygen has the orbital p orbital this, and p has the d orbital this. So it interacts through this, so it gives the electrons and it again accepts the electron. This is known as the back bonding phenomena. This is p pi d pi bond. This bond is p pi d pi bond, and this is complete sp3 structure because there are 4 bond pair, or so to say the 4 atoms which each phosphorus connected and no lone pair, so it is perfectly tetrahedral in structure, and this again is 190.5 degree. So yeah, this is the thing. The bond angle POP bond angle, this POP bond angle is 127 degree. In this case, this is a fact, you have to learn this. Now SiO2, when very another peculiar structure, SiO2 we can tell is the solid like diamond. I think the second hardest structure after diamond. SiO2 in the solid state, I should say, is something like this: SO O Si O. Here it is again O. Here it is O. So every silicon is bonded with 4 oxygen atom, and every oxygen is bonded with 2 electrons, 2 oxygen atoms. So this has the structure of, this is hybridization sp3. These are some important. This is in 3D. I am drawing it in 2D, but this is a lattice, complete lattice, which is coming out in 3D. So it has a hybridization of sp3 also. Now and there is a silicate also, some silicates. This structure also has an hybridization of sp3. So these are some peculiar structures that in the previous years the direct questions have been asked on these structures. So it's important that you know how to these structures are very important. So you have to remember how to draw these structures, or what are the conditions, or what are the formula you have to follow for drawing these structures. So yeah, first is the Si3O9. Si3O9. So in this central atom would be Si. You can apply the 4 conditions and calculate that. It comes out to be this. So I will represent Si by this and oxygen by the same oxygen. So if this is the Si, this is the oxygen, this is the oxygen, and this is the oxygen, this is the oxygen, and let me use 2 colors because it is a little bit complex. So this is one thing, this is the one part of this SiO, and there is a negative charge on here, negative charge on here also. Then here comes I think the formula given is wrong. It should be Si3O6 in case, because there are only 6. It should be 6. So here it is. Oh, sorry. It should be 9. So this is silicon, and this is oxygen. So this represents that one oxygen is coming out of the plane, and it has this negative charge. The silicon is not having a negative charge. There is one silicon here, and one oxygen is coming out of this plane. One oxygen here is a negative charge, and the one oxygen that is coming out of plane has this negative charge. So this oxygen, there is a silicon atom, and this again denotes that element. This is again an oxygen here, then an oxygen here, then here is another, that the same structure. Here it is, and here it is. So this is how this structure is on. The negative charge is here also, and negative charge on here, negative charge on here, and negative charge on here. So structure would be something like, we can say this. Join this, we can join this. So this is the structure of Si3O9 when the 3 electrons, the three oxygens are coming out of the plane, which are having this negative charge, and 3 oxygens, these are in the plane. So this the silicon atom has a hybridization of sp3 because 4 bond pair, no lone pair, hybridization sp3. So few points to be noted here is there is no OO bond in this here and no Si bond. There is only SiO bond present in this. So these are the examples of cyclic silicates. So cyclic silicates only have the SiO bonds, no OO bond and no Si bond. One thing is to be noted that oxygen which is being shared with which is making bond with two of the silicon atoms should not have the negative charge because it is fulfilling its octet or should fulfilling its minimum required conditions. So it should not possess the negative charge. The negative charge should be possessed by those for those 6 oxygen atoms which are bonded with only one silicon atom. Okay. Next important structure would be of B2H6. So to say B2H6, it's different from C2H6. This molecule does not have any BB bond as compared to C2H6. C2H6 has a CC bond, and hybridization, as you can see, would be sp3 because it has 4 bonds, no lone pair, sp3 hybridization. However, in B2H6 there is no BB bond. That's why it's different from the C2H6. Therefore, it would be something like this. This is a peculiar structure, a quite different structure from the rest of this. That there is a hydrogen, here is a hydrogen, and the 2 hydrogen lying here, and this boron, and this hydrogen, and this hydrogen. These are something like this, which means there are only 2 electrons in whole this area which are delocalized over 2 boron and 1 hydrogen atom, and same for the upper bond also. So this is something like 3 centers are there and only 2 electrons are being delocalized or delocalized here. So it is a different bond which is called as 3-centered 2-electron bond, or also known as the banana bond, as you can see from here. As you can see from here that a banana structure similar to banana is found. So this is the banana bond. So 3-center 2-electron bond because there are 3 centers and only 2 electrons are there. So it's a banana bond. So few of the properties regarding to this is that because this has the this is only there are 2 electrons are delocalized over 3 center, therefore it is bond strength is not as less as compared to this bond strength. This BH bond strength is more than this BH bond strength, and this bond length is also greater than this bond length. For example, this has a bond length of experimentally it is determined that this has bond length of 1.19 angstrom, and this has the bond length of 1.33 angstrom. Also, one thing is to be noted is that this is not a planar molecule. This one hydrogen lies above the plane of this molecule and one hydrogen lies below the plane of this molecule. So this is a non-planar molecule, not a planar molecule. This can also come directly in the J because it is a very famous compound and its structure is quite peculiar, banana bond. Other one is H2O2. H2O2 is something like this, that oxygen and this H comes here and this H comes here. There are 2 lone pair from here. Because of this lone pair repulsion, the bond length of OO, this OO is very weak bond, and its is 148 picometer, which is quite large as compared to OO single covalent bond length, and this is very unstable structure. It has a book-like structure, and this angle is also 94.48 degree because of this lone pair repulsion. It reduces it to 94.48 as compared to the H2O, in which it is 104.5 degree. So because of this repulsion, the bond length is larger, also this angle is smaller, so this is also directly can come in the JEE paper. Yeah. Then there is then we come to sp3d. So few of the points I have told you about the sp3d, that the d orbital that is being involved in the hybridization is dz square, and the electron, if the lone pair is to be placed, it should be placed at the equatorial position. First lone pair should come at the equatorial position, as well as the second lone pair would also come at the equatorial position because of the lone pair bond pair repulsion in the first case, because of the considering the lone pair bond pair repulsion in the first case and lone pair repulsion in the second case. According to that, if there one lone pair present, then the geometry is seesaw. If two are present, then the geometry is T shape. So these were the two things which I told you earlier. So let us consider two more examples. So if let's say we take PCl3 F2, so few of the points which are to be kept in mind, that more electronegative element will always come in at, or first I will say that there are few structure possible, that either this structure is possible, that Cl will come here and F, or P, F, Cl, this is one possible structure, and one of the possible structure can also be P. You can say both F are at the equatorial position, and Cl. So one of the rules is said that the more electronegative element should come at the axial position and the less electronegative element should come at the equatorial position. So we know that the electronegativity of fluorine is 4 on the Pauling scale, and of the chlorine is 3 on the Pauling scale. That is, F fluorine is more electronegative as compared to chlorine. Therefore, fluorine should be at the axial position. So both the fluorine should be at the axial position in this case. So this is the correct structure, and this structure is not correct. So in this case, I will tell you what the dipole moment is, but for the time being, the dipole moment of this is 0, or dipole moment, you can say the charge which is coming here and here, it is cancelling each other, and also this charge rotation is cancelling each other. So this is how we define. I will define dipole moment at the later stage, but I am just saying that dipole moment of this compound is 0. Again, one thing to be noted, that PCl5 in the gaseous state, if it is said the PCl5, what is the hybridization of PCl5 in gaseous state, then definitely PCl5 will have the hybridization sp3d and the geometry of trigonal bipyramidal. This would be the case, that it would have the geometry of trigonal bipyramidal. But however, if PCl5 solid is asked to you, then you have to keep in mind that PCl5 in the solid state exists as PCl4 minus or PCl4 plus, and PCl6 minus. So in that case, it is a tetrahedral and this is a square planar. So cationic form is in tetrahedral form and anionic form is in square bipyramidal form, not square planar, square bipyramidal form. So this is the thing you have to keep in mind, whether it is given as solid or whether it is given in gas. Same for the BeCl2 case also, because BeCl2 in gaseous state has the linear shape, but in the solid state it has the sp3 hybridization. For the PBr5, if you consider it gaseous form, PBr5 and PI5, again these are trigonal bipyramidal as far as their gaseous state is concerned, but in the solid state PBr5 and PI5 both exist in PBr4 plus and Br minus and PI4 plus I minus consecutively. So therefore its hybridization is sp3 in solid state. So these are some few of the things that you have to keep in mind, that which state is given of this. However, for PF5 plus, it's not the same way. It's not PF4 plus or PF minus in that case. Yeah. So next hybridization that we have to consider is sp3d2. So it has only 1/6 of the S character, that is, you can say 16.66 of the S character. So it is less electronegative than sp3d, sp3, sp2, and whatever hybridization we have talked about since now. This is the least electronegative, so to say. So yeah, few of the examples I have told you about SF6. Let's take new example, that is XeOX4 minus. It is few of the compounds in which the noble gas is reacting with oxygen. So XeO64 minus would have something like this, that xenon is forming 2 here, and O, and this O has a negative charge on it, and this forming a planar. So this is the structure for XeO6 minus no lone pair 6 bond pair sp3 due to hybridization square bipyramidal in shape. So now taking the example for sp3d3 hybridization, so it has only 1/7 of the s character less electronegative than sp3d2, and for one of the example for the sp3d3 is IF7, that is iodine IF. Its shape is in pentagonal, that is 5 are present here, something like this here, and these two are in the axial and these 5 are in one plane. These 5 are in one plane, so this angle is 72 degree and this angle is 90 degree. So 72 degree and 90 degree are the angles, bond angles in this. In this case, what you would say, where the lone pair should come? If first lone pair I have to keep in place, I should keep the lone pair definitely here, because if I keep it here, lone pair here, then there are only 2 bond pair at 90 degree repulsion. But if I keep a lone pair here, there are 1 2 3 4 5 lone pair bond pair repulsion at 90 degrees, so that would be quite horrible. So I will keep the lone pair in the equatorial position in this case also. Yeah, few of the facts also. XeF6, about the XeF6 in the solid state is found as the XeF5 plus and F minus format. These are the few of the facts that you have to keep in mind. So XeF5, F minus acts as a bridge between the lattice of XeF6 in the solid, something like this, that this is XeF5 plus and this is F minus, and this is acting as a bridge between XeF5 plus another XeF5 compound plus, and this is again F minus, and again this is extending. So one thing, what is the you will say the hybridization of XeF5, 5 bond pair and 1 lone pair on Xe, so it would be 5 plus 1 6, so it would be sp3d2, hybridization would be sp3d2. However, since there is 1 lone pair, so it would not be perfect square bipyramidal, it would be square bipyramidal, and the lone pair, you can place lone pair at any of the places in equatorial. There is no equatorial and axial position in square bipyramidal geometry. Yeah. And what about the XeF5 minus? In the XeF5 minus, you would have what would be the geometry? What would be the hybridization first? There are 5 bond pair, 2 lone pair, so 5 plus 2 7. So the geometry would be something like this, pentagonal bipyramidal. Instead of pentagonal bipyramidal, it would be pentagonal planar, because the 2 would be at the, you will say, the axial position. The 2 lone pair will come at the axial position in that case, because if XeF5 minus, we consider that in the IXC, or I would say in the XeF6, so to say, in XeF6 there was 6 bond pair and 1 lone pair. So xenon, the first fluorine was here, the second fluorine was here, 1 fluorine here, 1 fluorine here, 1 fluorine here, 4th fluorine here, and I said that it should come at the equatorial position. But now when we are talking about the XeF5 minus, that we have to consider the second introduction of the lone pair. It cannot come at the equatorial position, because if it comes at the equatorial position, the lone pair repulsion would be more, because their angle would only be a 72 degree. But in that case, if I place both the lone pair here, I have an increased number of repulsion, increased number angle, and the lone pair repulsion will be minimum. So the XeF5 minus have the structure of Xe here, and the 5 bond are something like this, which are in the same plane. These are all in the same plane, and 2 lone pair here and here, which are at the axial positions, and its geometry is pentagonal planar. Again, one thing about the ICL3 does not exist as such. ICL3 exists only in the dimer state, and in the dimer state it accepts electrons from the chlorine or the another which is connected to another iodine through the coordinate bond or dative bond, and the structure is something like this, that this is I and this is chlorine, this is here chlorine, this is chlorine here, and this is again iodine, then 1 chlorine here, 1 chlorine here, and one chlorine here. So this chlorine has lone pair, this chlorine has in fact 3 lone pairs. So it forms a, and this has vacant orbitals, so it forms a coordinate bond here, it forms a coordinate bond here. It again has 2 lone pair, it again has 2 lone pair. So 2 lone pair, 4 bond pair, it is a square planar in the shape, and the hybridization would be sp3d, 2 4 bond pair plus 2 lone pair. So ICl3 does not exist as such, but ICl3 exists in the dimer state, and obviously this length would be more, this bond length would be more because this strength is less than as compared to this strength. So it is said that it is around 2.72 angstrom as compared to 2.38 of this. So this is longer in size. Now this was all about the valence bond theory. Now there was one more theory which was proposed, and very important, is that molecular orbital theory. There was some confusion in that valence bond theory, is that the B2 is a molecule that is found to be paramagnetic, but if we follow the valence bond theory, it comes out to be dimagnetic. So in there, if we apply the molecular orbital theory, we found that the B2, the position of B2 to be paramagnetic is explained by the molecular orbital theory. So first, diamagnetic is the one which has no unpaired electrons, and paramagnetic is the that compound which has at least one unpaired electron. So starting with molecular orbital theory. Molecular orbital theory just says that if there is 2 orbitals which are going to be overlapped, then 2 molecular orbitals are formed, one which is lower in energy than this and one which is higher in energy than this. The one which is lower in energy is called bonding orbital, and one which is higher in energy is called anti-bonding orbital. Now the thing is that these orbitals, molecular orbital theory treats orbitals as the wave. So this indicates the summation of wave, that is the positive superposition. If this is psi m and this is psi n, so this is the positive superposition of the waves, and this is formed due to the negative superposition of the wave. So its antibonding orbital, the energy of antibonding orbital is higher than the individual individual atomic orbitals that have combined, and the bonding molecular orbital has the energy quite less than the individual atomic orbital. So if I have to draw a diagram something like this, that this is the wave, independent wave, something like this. This is for A, this is B, this is energy I have plotted, this is here is energy. So it would be something like this is independent wave for, let's say, phi A, this is phi B, independent waves, both are the independent waves. Then when these are combined, or there is a positive overlap takes place, the resulting wave would be something like this. This would be, so this density is always greater than 0, so the energy is less than the positive than the individual orbital, so this would be energy. And if the negative of this is taken, so something like this would be formed, that it would come here, and then it would go here, something like this would be formed. So this is the psi m, I would say. The probability of the electron to be found is determined by the psi m square. So all thing is positive, so definitely it would be positive. But in this case, the psi, if this is the psi m for the star, by psi m star I mean the anti-bonding orbital. So the psi m star square would be something like this, that it is coming here, then touching 0, then going over and touching here. So it would be something. So internuclear distance, that is the probability can be 0 also of presenting the electron to be present in the anti-bonding orbital. So this is how we define the bonding orbital and the anti-bonding orbital. So next we will define what is the order of energy for the anti-bonding orbital and bonding orbital, because we know that for that normal, if we do not consider the molecular orbital theory, there is n plus L rule, based on which we will define the energy level, or I should say that 1s is less than 2, 1s is less an energy than 2s, and then 2p So it is completely based on n plus l values. However, there is no n plus l values for this molecular orbital theory. So some of the conditions same, the combining orbitals should be little bit of the same energy, the energy should not be different, that is 1s should be, or 2s should be combining with 2p, 2s cannot combine with, or it has very less probability to combine with 5p or something like 4p in forming an atomic molecular orbital, and they should have the same symmetry about the axis. That means that if px is coming, then another should also be px. It should not be that px and py, the internuclear axis is the z axis, and let's say the px and pz are coming. Obviously one is along the internuclear axis and one is perpendicular to nuclear axis. They are not symmetrical to the nuclear axis, so they cannot combine according to molecular orbital theory. So types of molecular orbitals, I have told you about the bonding orbitals and anti-bonding orbitals. Now some of the difference, that there are also pi molecular orbitals and sigma orbitals as there are in atomic orbitals, that the one which combine as head-on is defined as the pi, defined as the sigma orbitals, and one is which adds the sideways are defined as the pi orbitals. So for pi overlap, the nodes of the atomic orbital should be perpendicular. Obviously, if you want to, if this is the axis and you want them to overlap, it should be perpendicular to them, but for the sigma orbital, it should be along the axis. The one thing that is important is that the pi bonding orbitals are ungyrated. Ungyrated would mean that if you rotate it across the internuclear axis, then the sign of it changes. For example, if this is the pi molecular orbital, then when this combine, then this is here it is plus and here it is minus. So if you rotate this around the nuclear axis, the sign would be changed, that is minus would come here and the plus would come here, that is the sign has changed. So it is determined as ungyrated. So pi orbitals, pi bonding orbitals are, so to say, they are bonding orbitals. So pi bonding orbitals are ungyrated and sigma bonding orbitals are gyrated. Gyrated in this case, that if two sigma orbitals are combining and if you rotate it around the nuclear axis, internuclear axis, the sign would still remain the same. For example, there is a 1s, there is a 1s, they combine, they form a large cloud of this type plus, let's say, and if you will rotate it around an internuclear axis, it would still be plus. So it is a gyrated because they are formed by the sigma, we would say the sigma bonding. So ungyrated pi bonding orbitals are ungyrated, sigma bonding orbitals are gyrated. However, the opposite is true for the anti-bonding orbitals, that is pi anti-bonding orbitals are gyrated and sigma anti-bonding orbitals are ungyrated. Fine. So energy level diagram for molecular orbitals. For molecules having atomic number less than, having molecular mass less than 14 or less than equals to 14, there is a different energy level, and for the greater than 14, molecular mass greater than 14, there is a different level. For example, if I have to consider for, let's say, less than 14, if I will say my compound has an atomic molecular mass less than 14, less than equals to 14, then the formula, then the energy will be 1s is less than 1s star, that is antibonding orbital of 1s, which is less than sigma 2s, which is less than sigma 2s star, now which is less than sigma 2pz. So in this case the z comes first, which is less than, here the pi 2px is equals to pi 2py, and this is less than sigma 2p, or sorry, this is less than the pi 2p x star is equals to pi 2p z star, and this is subsequently less than sigma 2p z star. So one thing to be noted, that if there are three orbitals of pz, px, py, so as low as the anti-bonding molecular orbital comes, the anti-bonding molecular is as high, because sigma 2pz has less energy than pi 2px and pi 2py, but its antibonding orbital has more energy than the pi 2px star and pi 2p star z. And sorry, this was for the compound which has the molecular mass greater than 14. So if you want to consider for O2 or for F2, something like this, you have to fill according to this. So if I want to write and for the compound less than equals to 14, the thing is, first is this sigma 1s, then sigma 1s star, then it is sigma 2s, then sigma 2s star, then the thing comes here that pi 2px is equals to pi 2py. This comes before the sigma 2pz. In this case, this comes before the sigma 2pz, and then it is less than the pi 2px star and is equals to pi 2pz star, and this which in turn is less than sigma 2pz star. So this from here the difference is for the compound which has the molecular mass less than equals to 14, and for the compound which has the molecular mass greater than 14, this is the change observed. So now I would write some electronic configuration for something in molecular behavior, and I will. So how do you define the molecule to be stable? So if the number of bonding orbitals, number of bonding electrons, by bonding electrons I would mean the electrons which are present in the bonding orbitals is greater than the number of anti-bonding electrons, then the compound is stable. If it is equal, that means it is not able to exist, and unstable if it is if NB or the number of anti-bonding electrons is greater than the number of bonding electrons. Yeah, so what bond order? So bond order is defined as the half into NB minus NA, where B is the NB is the number of bonding electrons and NA is the number of anti-bonding electrons. So bond order would be defined as that. Let's say bond order would mean that double bond or single bond. If there is a double bond between them, then bond order would be 2. If there is a triple bond, the bond order would be 3, something like this. So bond order is defined as the half into number of bonding electrons minus number of anti-bonding electrons. So the molecular orbital theory gives us the bond order, which is one of the merits over the VBT, which doesn't specify about the exact bond order. Yeah. So bond length will decrease as bond length. We can also compare the bond length, because as the bond order increases, the bond length decreases. So we can compare both bond order and bond length according to MOT theory, however, which was not possible as far as valence bond theory was concerned. So let us write some electronic configuration according to this MOT theory, keeping in mind the energy level which are defined for the compound which have the molecular mass less than 14, have different energy level to follow, and the compound having the molecular mass greater than 14 have the sigma orbital, the sigma 2pz before the pi 2px and pi 2py. However, it is the opposite in the compounds having the molecular mass less than 14. Yeah. So first is, let's say, hydrogen molecule. If you were to write for hydrogen molecule, you know the hydrogen molecule only have the 2 electrons, so it would be sigma 1s2. So no anti-bonding orbital comes into account. So bond order for the S2 will be half times number of bonding electrons, which are 2, minus number of anti-bonding electrons, which is 0. So bond order would be 1, which is also determined as far as VBT is concerned, because hydrogen is something, we draw hydrogen something like this, and we say that it is a single bond, so its bond order should be 1. Yeah. Again, then I will consider helium molecule. So helium molecule will have the 4 electron, so it would have the sigma 1s2, and then the next 2 will go into sigma 1s star, I should say 2. So its bond order would mean half into 2 minus the number of bonding electrons 2, and number of anti-bonding electrons are also 2, so it is 0. That is, it is unstable or it does not exist, helium, and we know that it does not exist because helium is a noble gas and it is highly unreactive, so helium 2 doesn't exist. Yeah. Again, then we consider the lithium molecule, Li2 molecule. What happens to Li2 molecule? Li2 has 6 electrons, so it would be sigma 1s2, then sigma star 1s2, then sigma 2s. 2s will come into 2. So number of bonding electrons are 4 and number of anti-bonding electrons are 2. So it would be bond order would be half into 4 minus 2, which will be equal to 1. So Li has a bond order of 1. Then Be2. When we are talking about the Be2, it has 8 electrons, so it would be sigma 1s2, sigma star 1s2, then sigma 2s2 and sigma star 2s2. So number of bonding electrons are 4, the number of anti-bonding electrons are also 4, so bond order would be half into 4 minus 4, that is equals to 0, that is beryllium 2 does not exist, or it is not a stable species. Now comes the structure which actually proves the existence of the molecular orbital theory, or which proves that the molecular orbital theory, which proves the merit of the molecular orbital theory, the electronic configuration of B2. As I have told earlier, that B2 has found to be experimentally paramagnetic, that it has unpaired electrons. However, as far as if we do it according to VBT theory, it comes out to be diamagnetic, that is all the electrons are paired. So what does for B2? B2 has 10 electrons, so it would be sigma 1s2, then it would be sigma star 1s2, then it would be sigma 2s2, then it would be sigma star 2s2. Now B2 has a molecular mass of 10, or I should say, I'm saying molecular mass, pardon me, it should not be molecular mass, it should be the number of electrons. Number of electrons 10, so wherever I have said molecular mass, replace it with the number of electrons. So number of electrons is 10, so we have filled 8 electrons, we want to fill 2 more electrons. Since its number of electrons is less than 14, so the electron will go into pi orbital, that is 2px, one only, because pi 2px and pi 2pz are both, pi 2px and pi 2py both are of the same energy. So these are the two unpaired electrons. Because of these two unpaired electrons, B2 is paramagnetic in nature and not diamagnetic nature, and its nature, its paramagnetism nature is explained by the MOT, and it's not explained by the Lewis dot structure or VBT. So this is the case. Now same can be done for the carbon molecule and for the nitrogen molecule, something like this, and you can just draw them. Now there is a concept called HOMO and LUMO. So HOMO we say is the highest occupied molecular orbital. In this case, the highest occupied molecular orbital would be 2p, and LUMO would be lowest unoccupied molecular orbital. So the lowest unoccupied molecular orbital corresponding to it would be the sigma 2pz. So this is the term HOMO LUMO which we follow. So in any case, if it comes, then this should not be a problem for you. These are only the terms. Now I will talk about the dipole moment. So our both VBT and MOT are clear. MOT questions on MOT just comes on this electronic configuration. What is the nature of paramagnetic or diamagnetic, something like these questions have come in JEE. So MOT is not been asked in detail in JEE, so I am not stressing that part that much. Now considering the polarity of bonds, that is a dipole moment. What do you know about the dipole moment? Obviously, because there is if there is a covalent molecule which has the difference in electronegativity, let's say I will consider HCl. Cl is more electronegative than H, then definitely the electrons will be more shifted toward the Cl as compared to the hydrogen. So Cl will develop a charge delta minus and hydrogen will develop a charge delta plus. Because of this, there is a dipole. Dipole always goes through from negative, from positive to negative. So there is a dipole moment developed, and this quantity is defined as dipole moment. So the unit of dipole moment is debye. The standard unit of dipole moment is debye, and 1 debye is equals to 1 into 10 raised to the power minus 18 ESU centimeter. So this is for the debye. So, and if let's say there is one dipole is something like this, one dipole is something like this, its magnitude is P, its magnitude is Q, and the angle between the dipole is theta, then the resulting dipole moment is equals to R underscore, the resulting dipole moment R is equals to the under root of P square plus Q square plus 2PQ cos theta. This is the resulting dipole moment. So this is how the dipole moment can be calculated if you know the individual dipole, the value of the individual dipole, and you know the angle between the two dipoles. Okay. So I will first give you some example of the molecules having zero dipole moment. Let's say CCl4. So here it is carbon, it's Cl, 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 4 bond pair, 0 lone pair, sp3 hybridization, tetrahedral in geometry. Every time when I will talk of any compound, I will talk about its hybridization, I will talk about its bond pair, its lone pair, and its geometry. By this way you can just easily grasp on how to calculate the geometry and the hybridization. So CCl4, so dipole, one dipole would be here, one dipole would be here because carbon is less electronegative as compared to chlorine. One dipole would be here, one dipole would be here, but as it is symmetrically placed, each at an angle of 109 degree from each other, these four dipoles, the resultant of these three dipoles come out to be exactly opposite to these dipoles because it is perfect geometry and its dipole moment is zero. So all the molecules which have the perfect geometry, or so to say zero lone pair, will have the dipole moment zero. I am saying all the molecules having zero lone pair, but the converse is not true, that if the dipole moment is zero, then the lone pair should be zero. This is not true, converse is not true, but if the lone pair are zero, then the dipole moment would be zero. Now consider that if you want to consider about HF, HCl, HBr and HI, how will you comment on the dipole moment? So first we know that the F is the most electronegative, then Cl, then Br, and then I. So that this X, let's say denoted by X, where X is a halogen, then you can say that Hx, there is a delta plus sign, there is a delta minus sign. So more electronegative the X would be, the more delta positive sign would be on the H and more delta negative sign would be on the X. And as this charge increases, we know that dipole is directly proportional to the charge, the value of dipole would be more. So HF would have the most dipole moment, then HCl, then HBr, and then HI. Now okay, so let's consider benzene. You must all know the benzene structure of benzene. It's something like this, and it's also represented as the circle in between. So here it is a chlorine and here it is a chlorine. So there is a dipole moment going here, and it on its para position, this is called its para position, there is again another chlorine. So these two dipoles cancel out each other and the resultant dipole moment of this comes out to be zero. Yeah, but let's say one example. So you have to comment on the dipole moment. Then let's say CS3 is there and Cl is there, and one is, let's say, CS3 and one is Br. So if you have to comment on these dipole moment, definitely this mu is not equals to 0 because this is sp3 hybridized, this is sp2 hybridized. Now I have said to you earlier that the sp2 hybridized orbital, sp2 hybridized element would be more electronegative than the sp3 hybridized orbital. So this is how you determine that this carbon would have delta plus on it, this carbon would have delta minus on it. So dipole instruction is from here, and since chlorine is definitely more, so the dipoles are same, and in this case also the dipole is same. So a very good illustration of that sp2 and sp3, how to determine the dipole position, that which carbon would have the delta plus the partial positive charge and which carbon will have the delta negative charge, because this has the sp2 hybridization and this has the sp3 hybridization, this carbon. So this is more electronegative as compared to this carbon is more electronegative as compared to this carbon, therefore the dipole moment should be something like this. So we know that these dipoles are not cancelling each other, or in fact if it would also be in other direction, then also the dipole moment would not have been 0, because this amount and this amount is different. So these are in the same direction. So this dipole moment is not 0, this dipole moment is not 0, and the mu1 is greater than mu2, because this value of this dipole moment would be greater than the value of this dipole moment. This is how we can comment on the dipole moment. So there is one trans N2 F2, you can say this is trans N2 F2. Trans would mean that the F are on the opposite side of this, and there is a lone pair here, there is a lone pair here. This is something like this structure. So this has the dipole moment 0, because this has the dipole moment 0 because this would cancel the dipole moment here, and this would cancel the dipole moment from here. So the resulting dipole moment of this element is 0. So this is trans N2 F2, I should say this is trans, and it is cis. If the fluorine, if you want to draw its cis isomer, then cis isomer would be N and F here, and dipole molecule. So this dipole is not 0, because this will give you some resulting dipole in this direction, not particularly straight, but I am drawing it like this, and this dipole will give you something in this direction, but the amount of this would not be equals to this. So this mu is not equals to 0, and this is cis N2 F2. So if it is a cis isomer of N2 F2, then its dipole moment is not 0, but if it is a transform of N2 F2, then its dipole moment is 0. So this is as far as dipole moment is concerned. Few important points about dipole moment is that the BF bond, it can be possible that the bonds are polar, but the overall molecule is non-polar, because you can see that here CCl bond is polar, but CCl4 on the whole is non-polar, because the resultant of these three dipoles cancel out this dipole. So some other properties is that if it is a polar compound, if it contains a polar covalent bond, but on the whole the dipole moment is coming out to be 0, this indicates that it is a symmetrical molecule. However, if it is a contains a polar covalent bond, but it mu is not coming out to be 0, then it depends that it has an unsymmetrical structure. So one more application of dipole moment is that we can predict the percentage of ionic character. So percentage ionic character in a compound is determined as the mu observed, that is mu observed experimental upon mu theoretical into 100. So this is the formula for determining percentage of ionic character in a covalent compound. So these are some of the applications or some important points about the dipole moment. So the next, this brings us to end of the dipole moment. So the next important topic is the resonance. What do we mean by the resonance structure? So resonance is it is observed that in ozone the double bond length is around 121 picometer, and the single bond length should be around 148 picometer. But however, experimentally it was observed that the length is 128 picometer, and both the bond length are equal. So this can be explained only on the basis of resonance. So let us define what is resonance. So for example, I will start with topic. Let's say for ozone, this is one of the structure. So this says that this should have the 121 picometer length, and this should have the 148 picometer length, and I think this is also identical, both are identical, that if we will draw it something like this, the negative, it has positive charge. If it is something like this, it is negative, it is positive, it is 121 picometer. Since bond order is more, bond length should be less. This is evident from here, which is in the which I said in the molecular orbital theory also. But what is observed is that there something like this, and this is 128 picometer, and this is also 128 picometer. So this can be explained through the concept of resonance, and the resonance is considered in the molecular orbital. So resonance is that the negative charge or the positive charge is not localized on this particular atom, it is delocalized on more than one atom. So if you will say, if I want to draw the resonance structures of ozone, I will draw it something like this, that this O minus, this has a negative charge and this is the oxygen. This electron density comes here, which shifts this electron density to here, so it has a resonance structure O plus double bond of O, then O minus, something like this. So these two resonance structures are identical to each other and therefore they both contribute equal, and the correct structure for ozone is this. So the stability, so each resonance structure contributes to the final structure of the molecule. So more stable the structure is, more would be its contribution towards the final structure. So let us consider the benzene ring. It's very famous benzene ring. So because of resonance take place, this shifts the electron density to here, this shifts the electron density to here. So its resonance structure, one of the resonance structure is this, something like this. So both these contributes equal because stability of this, this is as stable as this is also. So these both contribute equal to them, and we represent that, and it is because it is equally this, all the three electron density are equally distributed over these 6 carbon atoms. Therefore this represents that it is something like that. So let us take few more examples and how to draw resonance structure, because it is of great importance in organic chemistry also. Resonance structure, which determines the bond length order, sometimes bond length order, bond order is determined also by resonance structures. So let us take CH3, or I should say carbonate ion, CO3 2 minus, this is O minus, this is O minus. So I would say the electron density from here gets shifted to here, and this electron density gets shifted to here. So it would be something like this, that C O minus double bond O, and this is O minus. Again this electron density can shift to here, and this electron density can shift to here. So another resonance structure would be C O minus O double bond O and O minus. So its canonical structure or its representation would be something like this, that this is O, this is O, this is O, this has some delta charge, this is some delta minus charge, this has some delta minus charge, because all the three oxygen atoms are sharing equal charge, because all three resonance structures are same indeed and have the same stability, and this is shared on all the three oxygen atoms. This would be the resonance structure, complete resonance structure for this here, and this total has a charge of 2 minus. So bond order can also be defined as this in the terms of resonance structure, that bond order is defined as the total number of bonds that are involved in the resonance structure, total number of bonds involved in resonance structure divided by the total number of resonating structures. But however, this formula is valid only if all the resonating structures are of the same stability. If there is a condition, if there is a two resonating structure in which the stability of one is greater than the stability of the other, or both the compounds are not equally stable, then this formula will not work. This formula is working only if stability of all the resonance structures are same. So number divided by number of resonating structures. So in this case, the resonating structures have the equal stability. So the total number of bond pairs which are involving resonating structures are 2 plus 1 plus 1, that is 4 upon 3. So bond order would be 1.33. So each one has a bond order of 1.33. Okay. Yeah. So resonance energy you define as directly proportional to the number of resonating structure. More the number of resonating structure, more would be the resonance energy. It is directly proportional to the stability also of the molecule. More the resonating energy, more would be the stability of the molecule. Okay, so now the next topic and the important one is the hydrogen bonding. So we have talked about the hydrogen bonding when we are talking about the hydrolysis, in which the NH3 forms an hydrogen bond with the H2O and forms an ammonium ion and a hydroxide ion NH4 plus OH minus. So that was because of the hydrogen bond formation. So why does hydrogen bond formation takes place? First thing, the hydrogen is bonded to very electronegative element, then it develops quite a bit of a partial positive charge and quite this has negative charge. So another hydrogen atom which is again has some kuch delta plus and it has some delta minus, it would be get attracted towards it because of this, and this is called the hydrogen bonding. However, hydrogen bonding takes place only between hydrogen or fluorine or hydrogen or oxygen and sometimes hydrogen nitrogen. Other than this hydrogen bonding doesn't take place because it requires the other atom that is bonded to hydrogen to be very, very electronegative, so that this delta plus charge is considerable, so that it can be attracted to another atom having a considerable delta minus charge. So conditions required for H bond to be formed is that the lone pair should be present. A lone pair should be present on this electronegative element, and the size of the electronegative element should be smaller, because if the size of the electronegative element is bigger, this delta minus charge is distributed over a large area, so it's not concentrated, so it would not be attracted where the delta positive charge on hydrogen will not be attracted very good towards this delta negative charge. These are the two conditions, and one more condition is that it should be connected to more electronegative element. In consideration, it should be the oxygen, fluorine or nitrogen. The strength of H bond. H bond is not that strength because H bond is less. Strength of H bond is less than that of the covalent bond, because it is, you can say, dipole-dipole interaction. It is a form of a dipole-dipole interaction. This is a dipole generated. This is also dipole generated, and this dipole-dipole interaction is causing to be formation of H bond. So it lies something about between 5 to 10 kilojoule per mole. So if you will say the order of H bond, if you are given, let's say, oxygen, this, and here it is a nitrogen which has some lone pair, then it is an oxygen, hydrogen, and there is an oxygen, it has two lone pair, and if it is a NH, I would say NH and N, and here NH, and here it is O. Right? So this would have, there would be this interaction, because it has delta plus charge, it has delta minus charge, it has delta plus charge, delta minus, delta plus, delta minus, delta plus and delta minus. So since nitrogen is less electronegative as compared to oxygen, therefore definitely this delta plus charge would be greater than this delta plus charge, so it would be this strength of hydrogen bond would be greater than this hydrogen bond. The same applies for this case also. So we know for sure that this is greater than this and this is greater than this. So we have to compare between these two. Whatever the order comes between these two, the same order will be followed between these two. So the thing is that it is attracted to lone pair quite recently. So this is greater than this is in turn is greater than this in turn is greater than this, and this is in turn is greater than this. So this is the order of the H strength. So now H bonding can be of two types. One can be intramolecular H bonding and one can be intermolecular H bonding. So intramolecular H bonding would mean the H bonding is taking between place of the electronegative element is also present in the same molecule, and the hydrogen is also present in the same molecule. But in the intermolecular, two different molecules are attached by the hydrogen bond. So if I will say, let's take an example of intramolecular H bonding. So to say, this is a benzene ring and it has a COOH group, or so to say it has a CHO group, that is an aldehyde group attached to it. This is the aldehyde group and oxygen OH alcohol. So this is this. So here the interaction takes place and a 6-membered ring is formed. Therefore this is quite stable. So this hydrogen bonding, because it has a delta negative charge, it has delta positive charge, and it also has a lone pair and it is small in size. So this is formed, and this is known as the intramolecular. This is intramolecular H bonding, and this is orthohydroxybenzaldehyde. You will study about it in organic chemistry, I suppose. It has lower boiling point than its paraderivative. It will have the lower boiling point considering to its paraderivative, because paraderivative would have because it acts as a discrete molecule, and in this the same is not the case. Yeah. So one more example I can take of the persulfate ion, that is HSO5 minus, so to say. So it would have the structure something like this. The sulfur is here, double bond oxygen, one oxygen is coming here, one oxygen is coming here, one oxygen, one hydrogen. So it has 1 2 3 4, 1 oxygen is missing, so yeah, 1 oxygen is here. So it has something like this structure is 2 oxygen, this, and this has the negative charge, so this oxygen will be attracted towards this hydrogen, or I should say this, the negative charge should be here because it is more electronegative. This is more electronegative, so it has the hydrogen. So this is how this H bond is formed, and we can know 1 2 3 4 5 membered ring is formed, therefore it is stable. So intramolecular hydrogen bonding takes place only if 5 or 6 membered ring is formed. Now if it is forming 4 membered ring or 3 membered ring, the intramolecular H bonding will not take place. So it is also known as the persulfate ion, persulfate ion, because it is H2SO5. It is generated from H2SO5, which is a persulfate acid. So this was intramolecular H bonding, which I told you the necessary condition that it should form 5 or 6 membered ring. Now talking about the intermolecular H bonding, there are many instances of intermolecular H bonding. Intermolecular H bonding exists in water. You can say here the water here. So there is interaction because it has delta negative charge, it has delta positive charge. This hydrogen bonding takes place in water also. In HF also the hydrogen bonding takes place. There it is HF, but there is some peculiar way in HF. Let's say this is HF, so this is H, this is F, this is again H. So this angle is 120 degree, and now H would be something like this. So this angle, so it is formed in a zigzag form. HF in hydrogen bonding takes place in the zigzag form, and the angle between them is 120 degree. Okay, so this is few examples of intermolecular H bonding. Most in the alcohols also the intermolecular H bonding takes place because they are more polar. Now to end this topic, I will introduce some intermolecular forces, some types of intermolecular forces, or van der Waals forces. So there are 5 types of intermolecular forces, and I will first give you the most strong of that of intermolecular forces and go in the decreasing order. The first one is a ion dipole interaction. That means the ion is present, let's say Na plus, and there is a dipole, let's say O H2O, that is water. So it has a negative charge, it is an ion, it is a dipole, and there is an interaction. So this is an ion dipole interaction. Another one is a dipole-dipole interaction, which was between the hydrogen bonding. Is again, I said to you earlier that it is a dipole-dipole interaction because it has something like this. It is also generated through a dipole. The positive charge is partial positive charge on it is generated according to dipole, and the negative charge on this is also generated according to dipole. So this interaction between this, the hydrogen bonding, is type form of a dipole-dipole interaction. Another one is ion-induced dipole interaction, which would mean that because of the ion, the dipole has been induced, and then ion dipole interaction has been took place. Another one is dipole induced dipole interaction, which would be something like this, that this is HCl and there is a Cl. So in HCl there is a plus charge, then Cl it is a negative charge. So this negative charge will cause to develop a positive charge on this Cl, that is induced because of this dipole. There is a dipole induced in another non-polar compound, and this interaction is called the dipole induced dipole attraction. And the other one is the instantaneous induced dipole interaction, which is something like this, that delta plus and delta minus, and again this instantaneous dipole, according to this instant dipole, there is delta plus generated here and delta minus generated here, and something like this. So ion dipole interaction is the strongest of the all, then the dipole interaction, then ion induced dipole interaction, then dipole induced dipole interaction, and then instantaneous induced dipole interaction. This is how, and all these comes under the van der Waals force. So one of the one of the dominant structure of van der Waals force is that it is directly proportional to the molecular mass of the compound. So more is the molecular mass, more would be the van der Waals forces. So van der Waals forces are also directly proportional to the boiling point. These are the cases. Now I will just end it on the note of explaining one more topic, that is the acidity. How to determine the acidity of an acid. Acidity of an acid is determined by the number of hydrogens, or number of hydrogen that are attached to oxygen present in that. So in most of the acid it is equal to the number of hydrogen. However, there is, for example, in H2SO4 its acidity would be 2 because number of hydrogen present is 2. Let's say if I will take H3PO4, number of hydrogen present in this is 3, so its acidity would be 3. However, there is an acid H3PO3, phosphorus acid, this is sulfuric acid, this is phosphoric acid, and this is phosphorus acid. Its acidity is 2 because its structure is something like that, that here it is a phosphorus, it is a double bond, then there is an oxygen which is attached to hydrogen, then there is an oxygen which is hydrogen, and this is hydrogen. So this hydrogen is not acidic because it is not attached to the oxygen, because, and these two are the acidic. So its acidity is 2, but the other two has the acidity according to their hydrogen atom. So this has to be keep in mind, because this has been asked in JEE several times, that which of the acid has the acidity less than its number of hydrogen, or something related to this question. Let's move to the last topic of the chemical bonding, that is back bonding. It is an important concept as far as competitive exam as well as the board exams are concerned. So let's look at back bonding. So back bonding, let's first look at the definition of back bonding. And back bonding occurs between occurs in a molecule in which one atom is electron deficient and other has unbonding electrons, or you can say lone pairs. For example, if I would say BF3, so BF3, 3 bonding pair, no lone pair, so sp2 hybridized, trigonal planar in shape. So in BF3 we know the electronic configuration of boron is 1s2, 2s2 and 2p1. So after accepting one electron from each fluorine atoms, it again has a valence p orbital. So it has a valence p orbital, so it can accept electrons from fluorine which has 3 lone pairs on it, that is unbonding electrons. So it would be the Lewis structure of, or I should say the structure of BF3. So it has three unbonding pair of electrons on each fluorine atoms, and boron has one vacant p electron. So there is a sharing of electrons from fluorine to the boron from each side, and this is known as the back bonding. It is an electron deficient atom and it has the extra pair of electrons, that is unbonding electrons. So the electron deficiency is due to the incomplete pair of octet. So because of this back bonding, occurrence of back bonding, the bond length, or I should bond length decreases of BF because of the acquired of double bond character in this BF bond equally, and also the since bond length, bond order increases, bond order is between 1 or 2, so bond length decreases, bond order increases, bond length decreases, and bond strength increases. As we know, the bond strength of triple bond is more than that the bond strength of double bond, which is more than the bond strength of single bond. So bond strength increases, bond length decreases because of the increase in the bond order. Its order would be somewhat between, bond order would be somewhat between 1 and 2. It would not be perfectly 2, it is somewhat between 1 and 2. So all the fluorine atoms give equally are resonated with, equally give their electrons to that the boron. So you can say the final structure would be something like this, that here it is boron, here it is boron, fluorine, and this. So this would be the final structure of BF3. Now the extent of back bonding depends on the you can say the concentration of unbonding electrons, on the deficiency of the accepting electron, as well as the concentration of unbonding electrons on the electron donor. So if this is BF3, if in case if it is BaCl3, BCl chlorine is more in size than that in case of fluorine, so that you can say that chlorine will not give the electrons easily as compared to that of the fluorine. Therefore the back bonding is more in BF3 than in BCl3, then in BBr3, and then in Bi3. So this is all about the back bonding. So I have covered all the concepts which are in the chemical bonding. If you do not understand any concept, you can rewind the tape and look at it. Goodbye.